If you don't understand your quantities, you don't understand your project. That's not an exaggeration, that's a fact. Quantities drive schedules, contracts, estimates, procurement, and almost every domain of project management. That's why in this course, we're going to teach you exactly how to calculate all the key quantities on a construction project. We'll take you through civil quantity takeoffs, structural, building, MEP, so mechanical, electrical, and plumbing quantity takeoffs. This course on construction quantity takeoffs is broken down into 3 sections. In section 1, we'll talk about the fundamentals of quantity takeoffs. We'll define what they are and what they're used for, and how they're used across the life cycle of a construction project. In section 2, we'll look at some of the specific tools and techniques you can use to complete a quantity takeoff. And then in section 3, we'll go through detailed worked examples of all of the different types of takeoffs you'll need to be doing on a construction project. So, in detail, section 1, fundamentals of quantity takeoffs. We're going to be going through the principles of measuring quantities, the takeoff process, the different types of quantity takeoffs, a basic overview of construction drawings and specifications, and the basic mathematical skills you need to know to complete a quantity takeoff. In section 2, we talk about the different tools and techniques you need to master to complete a quantity takeoff. So we'll talk about the skills you need, the techniques you need to know, and some of the different software tools available that you can use to complete a quantity takeoff. Then we'll look specifically at Bluebeam. So Bluebeam's the quantity takeoff tool I use, and I think the easiest and best to use when you're doing quantity takeoffs of PDF drawings. We'll go through simply how to use Bluebeam and the basic measuring tools you need. Then in section 3 is where we go through in detail all of the different types of takeoffs for the different construction activities. We'll talk about earthworks, concrete structures, MEP, so mechanical, electrical, and plumbing, architectural, and other takeoffs. For each of these examples, we'll look at a set of engineering drawings and then go through an example takeoff to show you how to do it in practice. I get a ton of questions about certificates of completion. So, to get your certificate of completion for this course, you need to complete 100% of the content. If you haven't watched every lecture from start to finish and you haven't completed all the practice activities and quizzes, your course progress bar will not be at 100%, so you won't be able to get the certificate of completion. Only then, once you've done 100% of the content, can you get your certificate. You can use this course as professional development units. So whether you're doing this as part of PMP, so Project Management Professional through PMI, or whether you're applying for an engineering chartership, once you get your certificate of completion, you'll be able to upload this to whatever organization or portal to demonstrate that you've in fact done the course, completed the practice activities, and watched all the lectures. And then you'll be able to use these training hours you're doing here to contribute to PDUs through your organization. So a little bit about me before we get started. So my name's Tim. I'm a senior project engineer with almost 10 years of experience in the industry. On top of that, I'm a chartered professional engineer in electrical engineering and project management, and I've done my PMP. I started building these courses a couple of years ago because I thought there was a massive gap in teaching people the fundamental construction project management and engineering skills used on major projects. A lot of us study technical engineering degrees at university, where we learn all about the technical side of engineering. We learn how to design an electrical circuit or the foundations for a bridge, but no one teaches us about project management, which is if you're working for a major general contractor or construction company, these are the actual skills you'll be applying 90% of the time in your day job. And so these skills matter. Mastering these fundamental construction project management skills will lead to you getting promoted faster, doing better at your job, and overall enjoying your work more. Welcome to section 1, the fundamentals of quantity takeoffs. In this section, we're going to lay out the absolute basics of what a quantity takeoff is and what they're used for. Now remember in the promotion I said that quantities drive construction projects, and that is 100% true. In this section, we're going to explain to you how quantity takeoffs aren't just used for estimation, but they're used for scheduling, cost control, contract management, procurement. Effectively, your ability to do an accurate quantity takeoff will impact every single domain of construction project management, and the purpose of this section is to lay out the basics so you understand what a quantity takeoff is, the role of quantity takeoffs, and the general steps that you need to follow to complete a construction quantity takeoff. In this first section, we're going to start off with the principles of quantity takeoffs. Quantities drive everything on construction projects. So to begin with, we need to understand what a quantity takeoff is and why they matter. So what is a quantity takeoff? The simplest definition of a quantity takeoff is a detailed analysis of the drawings and specifications to determine all the materials we need to complete a construction project. A simpler way of thinking about this is taking a set of drawings, plans, and specifications and turning it into a detailed bill of materials or an itemized list of everything we need to complete the project. Examples of this can include reviewing the drawings to work out how many light fittings we need, the volume of earthworks, the lineal meters of trenching, the number of drainage pits, the total tons of steel reinforcement, or the area of masonry walls. So to complete a quantity takeoff, we first need to break the project down into all its specific sections. And then again, so for example, we'll break a project down into civil works, architectural works, structural works, and then against each of these subsections of the project, we'll document all the materials needed. So if we break the project down into earthworks, then we work out for the earthworks the total volume of cut and fill or the total volume of imported materials we'll require. So the inputs to a quantity takeoff will be the design drawings and specifications, and the output will be an itemized list of all the materials and key quantities that are needed to complete the project. Who uses quantity takeoffs? Well, firstly, project engineers need to be able to do quantity takeoffs. Estimators need to be able to do quantity takeoffs. So there's individuals who work out how much things cost. Contract administrators need to be able to do takeoffs for when managing contracts and setting up the bill of quantities in a contract. But also project managers need to be able to do it. Overall, quantity takeoffs are used by pretty much everybody on a construction project. Even the origins of the job role of quantity surveyor is someone who's employed to track and manage quantities. And by tracking and manage quantities, they manage costs, they manage value, they manage contracts, they manage risk, and they manage payment. Quantities is such a key driver of every individual element of a construction project. So why is this the case? Why are quantities such a key driver of every element of a construction project? Well, to answer that question, we'll look at the role of quantities in estimating, scheduling, procurement, contract management, project controls, and also design management. Estimating is the process of accurately calculating construction costs. And this is probably, when you think about it, the most direct link between a quantity and a project outcome. So if you talk about working out how much something costs, well, the cost of the work is always going to be directly proportionate to the volume of the work. So if we have to do 50 meters of trenching, it's obviously going to cost less than having to do 500 meters of trenching. So the quantity is a key input to the project estimate. Scheduling is the development of the project timeline, the plan of how we're going to complete the project and when activities are going to occur and the sequence they need to occur. And again, in the same way that the cost of a project is proportional to the volume of work, so the quantity, the duration of a project is also proportionate to the volume. So we think about our example of 50 meters of trenching versus 500 meters of trenching. Obviously, 50 meters of trenching is going to be much quicker to complete than 500 meters. So the quantity of work is also directly proportional to the duration of the work. Procurement is the process of acquiring the external goods and services we need to complete the project. Again, what we procure will depend on our bill of quantities. So if we need to buy pipes to install in our trench, well, the amount of pipe we're going to need to procure will be proportionate to the quantity. Again, this is all super obvious stuff I'm saying, but I just want to make it clear how the quantity of work is driving every individual element of the project. And so we need to be able to complete a quantity takeoff properly to be able to impact our estimate, our schedule, our procurement. Furthermore, we're actually going to use quantities to manage contracts. And while this link may not seem as obvious, but all the contracts we manage, whether how much we pay people, how much we get paid by our client, will always depend on the volume and quantity of work. So quantity is a key driver to any contract. So if we're talking about a subcontract, we might be paying a subcontractor to come to site and complete concrete foundations. If in their contract they have to do 20 concrete foundations, then the amount we pay them when they can submit their monthly payment claim, if they've done 5 concrete foundations, their contract volume is 20, then we'll be able to certify 25% of their payment claim because they've done 25% of the work. And again, a quantity is a key driver in managing the contract. Next, project controls is the cost and schedule management during the project. This is when we talk about earned value management and how we monitor and track costs and compare our planned performance against our actual performance. And again, quantities are a key driver of this function of project management. So if we look at, we need to understand the total quantum of work we need to do and compare this to how much we're doing versus how much we said we're going to do. If our original estimate of volume of work is wrong, then when we start measuring progress, we'll be measuring our completed progress and our percentage complete incorrectly if we initially estimated our quantities wrong. And finally, when we're talking about design management, so during the development of the project technical solution, we'll also need to track and manage the quantum of work. So if we're developing the design for a pipeline, at each design gate, we'll likely measure the total length of pipeline and try to keep it below a fixed quantity, because this means once we know we can keep it below this fixed quantity, we also know that we can complete the project scope within the original budget and schedule. So I know I spoke about some different domains of project management, but you should be able to see that quantity takeoffs aren't just an estimating function. Quantity takeoffs impact every single aspect of construction management. They obviously impact our estimate, but they also impact our schedule, how we manage our design, how we prepare our tender packages in procurement, and even how we administer and manage contracts. Being able to complete accurate quantity takeoffs is such a fundamental construction project management skill, and it impacts every single domain of the project. We can even simplify this and look at this across a project lifecycle, and we'll see we're going to be using quantity takeoffs at every single stage of our construction project. We'll be using them in the initial early stage when we're tendering the work and preparing our estimate. Then in the pre-construction phase, we'll be using quantity takeoffs during procurement and to manage the design. During the construction phase, we'll need them to manage the project cost, schedule and budget using project controls. We'll use them to manage contracts and approve payment claims, and then we'll even use them in the project closeout phase to measure our performance and update our estimating libraries. Next, I want to briefly talk about the difference between quantity takeoffs and estimating. So what's the difference between an estimate and a takeoff? Well, they're super related concepts and very, very similar, but there's an important distinction. A quantity takeoff is purely about measuring. It's about working out how much of something we have to do. Estimating takes us a step further and applies a cost to a quantity. And a fair question to ask, well, what about labor and plant quantities? Aren't they something we should calculate when we're doing our quantity takeoffs? So if we want to calculate labor and plant quantities, what we need to do is we take the quantity of work and we apply a production factor to this based on a methodology. For example, if we go through the design drawings and we measure that there's 1,000 meters squared of formwork we need to do for our concrete structure, at 2 man-hours per meter squared, this gives us 2,000 man-hours of labor, and that is the labor quantity for the project. Some would argue that this measuring of the labor quantity forms part of the quantity takeoff, and to calculate it, it depends on our methodology and resourcing. But this methodology and resourcing can vary. So for example, if you consider a concrete wall and you're trying to calculate the plant quantities needed to complete it, well, you could either use 1 scissor lift or you could use 2 scissor lifts. If you use 2 scissor lifts, it'll also impact your labor, because if you're working with 2 scissor lifts, you'll reduce the duration that you need labor to complete the wall because you've got to complete both walls in parallel. That's why the way I think about it is I don't think of labor and plant quantities as part of a traditional quantity takeoff, because they depend on the methodology, they depend on the staging of the works, and they depend on our resource leveling. And ultimately, they're subjective quantities. We can go through the design drawings and measure that we need 1,000 meters squared of formwork. However, If we then decide we're going to be using 2 crews as opposed to 3 crews, then it'll impact how much scaffolding we need. Then suddenly we're applying all these subjective elements to the measurement based on our methodology. That's why I like to think of a quantity takeoff as an objective measure. It's purely measuring the volume of something we need to do. So that's why, in my opinion, when I think of a quantity takeoff, I think of it as purely the objective quantities of the work we need to do. And so when I talk about quantity takeoffs in this course, I'm purely going to be looking at the objective quantities that we need to complete our project. If we're talking about estimation and cost estimating, then we need to apply a delivery methodology to this. And this is where we start to get into subjective areas. And that's where estimating becomes, and when we talk about estimating, it can become almost more of an art than a science. To be a good estimator, you have to understand the methodology, the sequence of the work, the schedule, and all these other external inputs. But in this course, when we're talking about a quantity takeoff, we're going to be talking purely about measuring quantities. So just to quickly summarize what we spoke about. We spoke about what quantity takeoffs are. So we define them in the process of taking a set of drawings, measuring all the key quantities and producing a bill of quantities. We spoke about what they're used for. So we spoke about how they're used for estimating, scheduling, procurement, contract management, and design management. And we spoke about the difference between estimation and quantity takeoffs. And specifically that if we're going to extend our quantity takeoff to talking about measuring labor and plant, then I would define that this falls into the realm of cost estimation and outside of what a traditional quantity takeoff is. All right, next, we're going to talk about the quantity takeoff process. Let's cover the steps you need to complete a construction quantity takeoff. This is going to be the basic process you need to follow to complete any sort of quantity takeoff. So we're not going to make it specific to civil, electrical, or mechanical, and we're going to not make it specific to procurement or to estimating or to scheduling. This will just be a generic process you can follow for any sort of quantity takeoff for any sort of scope. The takeoff process is super simple, and I'm probably making it more complicated than it has to be by setting it out like this. But this is just meant to give you an idea of what steps you need to follow to complete a takeoff. So to begin with, you need to review the project documentation. You need to look at the drawings and specifications and get a high level of understanding of what you're going to be measuring. Next, you need to set up a takeoff structure. So this will be an Excel document or some sort of table that you're going to fill out with your quantities. Next, you need to find a tool to use to complete the takeoff. So this can be a software tool, or this could be simply measuring by hand with a ruler, the old-fashioned way. Then you're going to measure and quantify the key items in your takeoff, and then you're going to finish by reviewing, checking it's correct, and adjusting as required. And now we'll quickly go through each of these steps in a little bit more detail. So the first thing you're going to do is you're going to review the design documentation. You need to look through the drawings and specifications and make sure you understand what it is you need to measure. You want to go through all the drawings, you want to look at the specifications, and you want to understand what the key information is, the purpose of the takeoff, the information you're looking for, the accuracy you need to find, and the format. So for example, if you're doing a takeoff of a concrete structure, you want to check all the drawings to make sure you understand where all the concrete structures are you're going to be looking at. So using an example, imagine you're a project engineer on site and you need to order concrete for the raft slabs shown on the screen. Your goal would be to measure the volume of concrete very accurately, and then you want to apply a wastage factor to that, because if you're ordering concrete, the worst thing you can do is underorder. So you want to make sure that you're measuring the minimum volume and then adding on a wastage factor, so when it comes to the concrete delivery, you're not ordering less than you need. So to do that, so you've reviewed the documentation, you understand it's a structural slab. The key information you're looking for to place the order is the volume of concrete and the type of concrete. The purpose is to place an order for concrete, and for your accuracy, you want to order greater than the volume you need and definitely not less than. So it's important when you're looking for the key information is you need to understand what the quantity is going to be useful. So if it's being used for an estimate, it's going to be different to whether it's used for procurement. So for example, say you're doing a formwork takeoff of structure. If you're doing it to order formwork, that's going to be slightly different to if you're doing it for an estimate. So for example, if you're doing it for an estimate, you'd want to be able to break down the quantity of formwork used for slabs versus the quantity of formwork used for walls. When if you're doing it to simply place an order for total meter squared of formwork, that might not be an important distinction, because if you're just talking about ordering the meter squared of formwork, you just want the total meter squared for the project. But if you're talking about it for an estimate, then you'd want to distinguish between walls and slabs, because you might have different production rates for these different types of structures. That's why one of the most important things you can do when you're doing a quantity takeoff is you need to understand what the information is you're getting and what it's going to be used for. And if you want to use a general principle, it's better to break your quantity takeoff down into more detail, because someone can always look at it and summarize it later. When if you just take high level quantities and you don't break it down enough, then if it doesn't have the detail they need, then you're actually going to have to go back and redo it. So I would say, as a general principle, well, firstly, understand what it's going to be used for. But then also, if you don't exactly understand what it's going to be used for, always err on the side of adding more detail to the takeoff, because you can always summarize and remove it later. Step 2 is to set up a structure that you're going to record your takeoff. So this is getting an Excel spreadsheet and listing out what are all the items you're going to measure. So for example, if we're talking about the concrete slab we were looking at before, we might break it down into the north-south ring beams, the east-west ground beams, and the slab. But it really depends exactly what you're going to be measuring. For us, we just want to get the total meters cubed of concrete to place an order. So we don't even have to break it down that much. But a simple way of measuring it would be just to have the ground beams and the slab as the two measurements we take. Step 3 is we want to find a tool to measure our quantities. So this can either be done manually, where we simply get the drawings by hand, use a scaled ruler and measure the dimensions, or we can use a software tool. I personally use Bluebeam for my takeoffs, and I'll give you a basic overview of how to use Bluebeam later on. But for now, you just have to find a tool you can use to measure all the dimensions and key quantities. Next is you just measure the quantities. Simply, the takeoff structure you set up before, simply go through and input all the measurements you recorded. So if you took the ground beams as one, you'd get the length, width, and depth of the ground beams. And for the slab, you just get the depth and the area of the slab, and that's all you need. You'd be able to calculate those together, apply a wastage factor, and then you'd get your volume of concrete. The final step is to review and adjust. You want to do a high-level check that your takeoff's correct. So for example, if you've done the takeoff with the concrete needed for that slab and you get like 0.5 meters cubed, it obviously doesn't make sense. It's way too small. Or if you get 500 meters cubed, it's probably not right either. So you want to do a high-level comparison and check that your quantity makes sense. You also want to do a check for errors and omissions. So again, go back, look at the drawings, make sure everything's accounted for. With the larger quantities, you could do a full spot check and check the quantities and measurements again. But overall, you should do a check at the end to make sure what you've calculated is correct. Then you also just want to maintain your quantity takeoff, and if there's any changes, say the depth of the slabs increase, say for example you're placing an order for the concrete, but then you find out that they've over excavated the ground beams, then it's simply a matter of adjusting your quantity takeoff, which if you set up the structure correctly would be very, very easy to do. So to summarize, I've probably taken it as something super, super simple and made it out to be more complicated than it is, but quantity takeoffs are super easy. The 5 steps we need to follow to complete one is to review the drawing and specifications to understand exactly what we're going to be measuring and what that information is going to be used for. We need to set up a structure for recording all the key items. We want to find a tool that we're going to use to measure the quantities. Then we're going to measure the quantities, and then we're going to review and adjust. That's it. That's all you need to do to complete a quantity takeoff. And again, I probably shouldn't have made it into this 5-step process because I'm probably just overcomplicating it a lot more than it has to be done. But quantity takeoffs are really, really easy, and that's all you have to do. Next, let's talk about the different types of quantity takeoffs. In this section, we're going to understand the different categories of quantity takeoffs that are used on construction projects. We'll categorize quantity takeoffs based on the methodology used to complete the takeoff, the discipline, So the area of focus, so whether it's civil or electrical, and then also the level of accuracy. There's really two different methodologies we can use to complete a takeoff. There's a manual takeoff. This is where we print out a copy of the drawings and using a scale and a ruler, we measure every quantity by hand. Or there's a digital takeoff. So this is where we use a software tool like Bluebeam or even a more advanced quantity takeoff software, and we measure all the quantities on the computer with a specialized tool. Quantity takeoff software is specialized software for completing quantity takeoffs. So these automate the process and they're basically quicker and more accurate. So examples of quantity takeoff software are Autodesk Quantity Takeoff, PlanSwift, Bluebeam Review, which I'll be talking about a bit later because that's the tool I use, and CostX. Next, we can categorize quantity takeoffs based on the different discipline. So this is the category of construction work they involve. So whether it's civil work, electrical work, mechanical work, structural work, there's slight nuances and differences in how we complete a quantity takeoff. The overall process will remain the same, but the specific quantities that we're measuring will vary. The different construction disciplines we're going to talk about when looking at quantity takeoffs are earthworks, concrete structures, MEP, mechanical, electrical and plumbing, architectural works, and other items. So things like temporary works and scaffolding. So the next way that our quantity takeoffs will vary will be the level of accuracy. So the level of accuracy will vary depending on the stage of the project and availability of information, but also the purpose of the takeoff. The available information, it's going to vary based on the level of design information. So as the project progresses, as the design gets developed, there's going to be more and more information. So our quantity takeoff is going to be able to get more and more accurate. It really depends as well the purpose of the takeoff. So if it's for a conceptual level 4 or level 3 estimate, which is really a high level plus or minus 30% estimate, then our quantity takeoff doesn't have to be super specific. So for example, if we're estimating the cost of a concrete foundation, we might be able to use a high level figure for tons of steel reinforcement based on the volume of concrete. However, if we're trying to actually procure the steel reinforcement needed for the structure, then we're going to need something more accurate. So we'll need to actually measure all the bars and calculate the tons of steel. So the level of accuracy our quantity takeoff can have will depend on the design information. So design is always developed in stages, where you start off with a concept design, which is really a high-level outline of the project that might be used in the early stage project development and feasibility study. Then you'll get a schematic design, which is a more detailed set of plans and drawings that might be used to procure a contractor. And then you've got detailed issue for construction design drawings that show exactly what we're going to be building and exactly where everything goes. So if we're talking about how accurate our quantity takeoff is going to be at each of these stages, at a concept design stage, our quantity takeoff is probably going to be between negative 25% to plus 75%. When it's at schematic, when we've got schematics, it'll be negative 15% to plus 30%. And then when it's detailed, it'll be from negative 5% to plus 10%. When we're missing all the available information we need, there's some things we can do to try and improve the accuracy of our quantity takeoff. The first is we can use parametric estimating. This is where we don't know the exact quantity for our project, but we can adjust other project estimates and accurate information we've got on other projects by a comparable factor. So for example, if we don't have a detailed steel reinforcement drawing for our project, we could know from another project they have a similar concrete foundation, then we could simply adjust by the volume of concrete to get the tons of steel using the same parameter. Or for example, if we don't know how many linear meters of trenching there's going to be on our project, we could look at another similar project and use that. That way we can make accurate estimates without available information based on other project data. And we can use other comparisons from past projects. To improve our accuracy, we should always try to overestimate rather than underestimate. If we start underestimating, this will start to have impacts on our schedule estimates, our budget estimates, and we always want to be high with our estimates rather than low. To further improve our accuracy, if we have an understanding of the underlying design principles, then we can make extrapolations. For example, if we're estimating the number of foundations we need, if we understand that the number of foundations is driven by the number of a certain type of equipment, then we might be able to quickly find out how much of that equipment is needed and then fill out how many foundations are needed. If we understand the fundamental design principles driving the design development, we can also improve the accuracy of our quantity takeoffs when we've got limited design information. In summary, we spoke about the different categories of quantity takeoffs. We spoke about how they vary based on the methodology, so whether we do a manual takeoff as opposed to a digital takeoff. We spoke about how they vary based on the discipline, so if we're doing a civil takeoff versus an electrical takeoff versus a mechanical takeoff. And then we also spoke about how they vary depending on the level of accuracy. So if we're doing a quantity takeoff at an early stage concept design versus if we're doing a quantity takeoff with finalized issue for construction drawings. Next, let's talk about how to read and interpret engineering drawings by looking at typical structure of an engineering design and the types of design documentation you'll be using. The different types of design documentation you'll be using include drawings, specifications, schedules, reports, and if you're working on a modern construction project, digital models. So things like BIM and 3D models of a structure. Drawings are used to provide detailed information about what we have to build. So if you've ever heard the saying, a picture tells 1,000 words, then that definitely applies on a construction project. There is no way to describe a bridge, a road, without a drawing. If it would be pages and pages of information, it would be so open to interpretation. So architectural and engineering drawings are used to explain exactly what needs to be built. Drawings show lots of different information. They show different layouts, geometry, how things connect together, and different detailed sections. And overall, the drawings should show us, as construction managers, exactly what we need to be building. And not all drawings are the same. There's lots of different types of drawings we'll be referring to on a construction project. There's title pages, there's general notes, there's layout and plan views, there's section views, there's schematics and symbols, there's schedules, and then there's project-specific requirements. And we need to be able to understand all of these different drawings and how they work together to paint a complete picture of a project and what we're going to be building. So the first thing to note when looking at a set of engineering drawings is the title block. The title block tells you who created the drawing, what the drawing is, the date the drawing was created, the stage of the drawing, so whether it's at 30% design, 70% design, 95% design or IFC, and then also the type of drawing and the drawing reference number. All this information is found on the title block. Then we've got our cover sheet. So a cover sheet is generally the title of the project and maybe an overall schematic view. And these drawings are often quite helpful to look at to understand the overall orientation of the project and how everything comes together. And often, whether it's on the title block or the page after, you get a drawing register on a design package. So this is a list of all the separate drawings in the design package with the drawing reference number. It's like a table of contents in a book. So that's another really useful thing to look at when you're first looking at a design package. Then we've got our general notes. So general notes are like a set of applicable notes that apply to every drawing. I say we're looking at a structural design package, the general notes will say things like what type of concrete's used, minimum cover to have on concrete structures, and they basically provide additional detail that would be monotonous, that'd be too much to put on every single drawing page. For example, if you need 50mm cover on all the reinforcement, they wouldn't say that on every single drawing, they just say that in the general notes. So it's always good when you first look at a design package to look through and understand what's in the general notes, because there'll be lots of little specifics to a project that get captured and summarized in the general notes. The next drawing type we need to understand is the layout or plan view. So the layout or plan view is an aerial view of the project. And typically you also have north-south or east-west grid lines which show how the project's broken up. And so the layout or plan view is a really good way to understand where everything is. So if you're looking at a building, it'll show you each room, the walls, the orientation, or if it's a road project, it'll show you the orientation of the road, where the intersections are, where the turns are, those sorts of things. So the layout is just like a really good drawing to look at to get an overall orientation of the project. And then it'll also have these cuts in it. So it'll have little cuts that say D or A, and that refers to a section view. And typically under that, there'll be an annotation with another number. And this number will be the drawing number that the section view's on. So then you can go and look at that section view to understand that information in more detail. So you can see on the example drawing shown on the screen that section D refers to a drawing number, and then it says that it gives you a cut of section D showing the 2 levels of the slab. Now this would be information it's impossible to see from the plan view, but you can see if you look at the section view, which is a cut of the 3D model or the cut of the 3D structure, that you can see that it's a slab stepped down into 2 levels with a wall. So if you look at the plan view, then you'll be able to note which section views give you more relevant information. Next, we've got schematics or symbols. So this is more typical for electrical, mechanical, or plumbing drawings, that they'll show you a layout of a, say, like a electrical single line diagram or a hydraulics drawing, and then there'll be a set of symbols that show what each item represents. So if you look at this as an example of a plumbing drawing, you've got a schematic showing how all the pipework interconnects, and then a symbol to represent what each of the different mechanical items is. Next, we've got schedules. So schedules are a good way of summarizing a lot of information into a small table. So for example, we've got a footing schedule on one drawing, which there's an annotation for each different type of footing. So maybe on the plan view, that will show you all the foundations. That will say F1, F2, F3, F4. Then you can go look at the schedule and it says F1 is a 2500 by 2000 by 900 deep footing with 2 layers of steel reinforcement. So rather than having to do a single drawing for every footing, they simply summarize. They'll have a layout drawing with all the different types of footings, and you can go to the footing schedule to understand in more detail what each footing is. Similarly, with a landscaping design, got a hardscape schedule, which has the different codes. So they might have a plan view that shows all of these different symbols. And then against that, they'll have exactly what the product they're referring to is. So schedules are a really good way of interpreting a lot of design information. Specifications often supplement design packages. So you might have an Earthworks design package that shows profiles and cut and fill diagrams, but then it refers to an Earthworks specification. And this provides more clarification as to design requirements and how things have to be built. And it's more important when you're understanding quality assurance and tolerances and the construction methodology. When you're doing a quantity takeoff, typically specifications won't be as applicable. It's much more about the actual drawings and understanding the different volumes and measurements. And in some instances, schedules won't be shown on the drawings, but they'll also be in the attached specifications or as a separate document. So they might, for an architectural project, for example, they might list all the products they're proposing to use in the architectural schedule. And so this can be useful when interpreting and understanding the design requirements. They might say wall type 1 is used, but then you go into the architectural schedule and they say wall type 1 is made up of brick with a certain color paint. And so they're just another good way of interpreting in summarizing design information. And then finally, when a design is produced, typically the architect or engineer will produce a design report. A design report is a document that explains how they developed the design, and they discuss the design rationale and the basis of design, the key decisions they made, how they engage stakeholders, and also safety and design. And this is a really good document to go to, particularly if you're trying to do a quantity takeoff at the early stages of a project when there's still insufficient design information. You can use it to fill in gaps by understanding the design rationale. But often when you're doing a quantity takeoff, you probably won't need to look at the design reports, but it's still useful to understand what they are. And then finally, the last bit of design documentation needed to understand are 3D models. For typically complicated structures like buildings, tunnels, underground train stations, or complex mechanical and electrical processing plants, more and more you're seeing 3D models being created. And this is because they're just too complicated to look at on a set of drawings and plans. You'd end up with hundreds of different section views showing how everything goes. So pipework doesn't clash with cable tray, which doesn't clash with a HVAC. And so 3D models are used to basically detect clashes and detailed every turn, every orientation, every wall penetration to show that all these different services can actually be built and fit into the space. And so if you're working on a project like a building or a train station or something with a lot of services and clashes, then you're going to need to be able to look at and use a 3D model to complete your quantity takeoff. So Typical examples of 3D representation will be with software like Revisto or Navisworks. So depending on the type of project you'll be working on, you'll need to understand how to use these models to complete your quantity takeoff. All right, let's talk about the basic mathematical concepts you need to be able to complete a quantity takeoff. I almost couldn't decide whether to include this section in the course because the mathematical concepts you need to complete a quantity takeoff are so simple. Basically, if you've done year 8 maths, then you'll more than understand the level of maths you need to complete a quantity takeoff. The maths is really, really simple. The hard part is understanding the drawings, understanding the specifications, understanding the specific quantities you need, and understanding what the information is going to be used for. But the maths, if you're not good at maths or you're not comfortable with complex arithmetic, then don't worry, you can still very, very easily complete a quantity takeoff. The basic math skills you're going to need to master to complete a quantity takeoff are arithmetic, units of measurements and conversion, geometry, algebra, trigonometry, very, very basic trigonometry, scale and proportion, percentages, and rounding. That's it. And that list is probably an exaggeration from what you're actually going to need to know in practice. All right, so arithmetic. You're going to need to know how to add, you're going to need to know how to subtract, you're going to need to know how to multiply, and you're going to need to know how to divide. That's about as complicated as it gets. You need to be able to take dimensions and get areas and volumes, so you'll need multiplication, and you'll need to take unit quantities to get total quantities using multiplication. Next, you need to understand the different units of measure that quantities will be in. So if a quantity is in millimeters or centimeters or meters cubed, to convert between imperial and metric, and basically just how to convert between different quantities. Then you need to understand the different geometry formulas for area and volume. Be able to calculate the area of regular and irregular shapes. So for example, a square or a rectangle, the area is by the length multiplied by the width. If you've got a triangle, the area is a half by the base by the height. But again, these are all really, really basic, and you can find the correct formulas in 2 seconds with a Google search. Then you also need to be able to know volumes. So if you've got a big rectangular slab, then the volume is going to be the area by the height. Again, you can just very simply find any formula you need using Google, and also perimeter. So if you've got a boundary fence, how do you work out the perimeter of the fence? Again, these are just all super, super basic concepts. Next, you're going to need to know some very basic algebra. I almost couldn't decide whether to include algebra because I feel like I'm overcomplicating something that really isn't that complicated. But in some instances, you're going to need to be able to reverse engineer quantity, which basically is what algebra is. So it's solving for the unknown. So for example, if you know the total meters squared of formwork and you know the total meters squared of wall formwork, then you could work out the total formwork less than 0.3 meters high by subtracting one from the other. Algebra is basically solving for the unknown. And calling it algebra is probably making it out to be more complicated than what it is, but basically, you need to be able to know how to solve for the unknown. And you're also going to need to know some basic linear functions. So these are just proportionate functions. So for example, if you have 10 meters squared of formwork in one wall and you need to calculate the quantity for 10 walls, then you just multiply it by 10. Again, calling it algebra is probably exaggerating a bit, but it's just basically very simple linear functions. The next is a very basic understanding of trigonometry. And again, you're not really going to need to use this much, but it's basically when there are missing dimensions, how to solve for the unknown. So if you get, say, 2 sides of a triangle and you want to work out the length of a beam from one corner to the other, you'll need to know a really basic trigonometry function. But I'm not going to walk through how to do this in this video, but you can very quickly and easily find this stuff on Google. So if you Google how to solve the unknown side of a triangle, it'll take you to a website that gives you a trigonometry calculator. Next, you need to be able to know scale and proportion. Now, scale and proportion can be confusing, but not because of the math side of things. Scale and proportion is very, very simple concept to understand. So if you have on a drawing, there'll be a scale that says 1 to 100, 1 to 200, 1 to 300. Basically, it means for every unit you measure on the drawings, in the real world, it's 200, 300, or whatever times the scale is that in real life. So for example, if you have measure something that's 1 centimeter on a drawing and the scale is 1 to 100, in the real world, it's 1 meter. Now, if the scale you use to measure something is wrong, the quantity takeoff will be wrong. And that's why scale matters so much. The other concept to understand is proportions. So this is useful when you're doing a parametric takeoff, that if you measure all the lights on one floor, then you can get the total number of lights on 10 floors by simply multiplying it by 10. Again, these are all sort of variants of addition, multiplication, subtraction, and division. And so if you understand those, then it's really just applying them in lots of different ways. And like I've said, the maths is very, very simple. You also need to be able to understand percentages and how to use them. Now, percentages, again, you're going to use in a variety of different ways when you're doing quantity takeoff. Use percentages to calculate how quantities change through design development. So the percentage increase or decrease in quantity. You could use them when you're applying wastage factors, or you could use them when you're applying risk factors. Now, percentages are really, really simple. So say you measure the volume of concrete in a slab is 10 meters cubed and you want to add on a 10% wastage. All you do is you multiply that by 1 plus the percentage divided by 100. So if you're adding on a 10% wastage, you multiply the 10 cubes of concrete by 1 plus 10 over 100, so by 1.1. So 10 meters of cubes of concrete with 10% wastage is 11 meters cubed. But again, if you struggle with that, just simply Google how to do it. There's tons of good resources explaining super simply what you have to do, but it's really just basic addition and multiplication. And the final mathematical concept you need to understand is rounding. So basic rounding of numbers. So if you end up with, say you measure something and it's 9.5 meters long, you round up to 10. If it's 9.4 meters long, you round down to 9. Now in general, when you're doing a quantity takeoff, you're never going to round down, because then you'll be underestimating the quantity you need. When you're talking about rounding, probably the biggest application we'll see of rounding is when you're talking about units of material. So for example, if you're measuring the length of conduit you need in a 100 meter trench, but conduit's only sold in 6 meter lengths, then the minimum amount you can round down to is the closest 6 meter length. So that'll be multiple of 6 greater than 100. So that's really to get accurate quantity takeoffs, you need to understand the material units. And that's probably the biggest application you'll see when you're talking about rounding. Overall, there's an expression I love when talking about quantity takeoffs or estimating or construction management in general. You can be precisely wrong or roughly correct. Now, the way I like to think about things is you always want to try and be roughly correct. So if you find yourself doing super complicated maths and equations to calculate something, you're almost certainly going down the path of being precisely wrong, where you're trying to calculate something way too accurately in way too much detail, and you're probably missing the bigger picture. As opposed to being roughly correct, where you're basically looking at the key information and extrapolating it out and filling in the blanks. That's the way you always want to be. You always want to be roughly correct with what you're going to do, because in practice, things are always going to be slightly different. Your wastage amount's going to be different. The volume of work's going to be slightly different. Something will change in the design. So if you try to get way too smart, make things way too complicated, people just aren't going to understand what you're going to have done. They're going to think you've done it wrong. So, and when you're thinking about the maths that you use when you're doing a quantity takeoff, it's very much the same concept. It's really, really simple. Addition, subtraction, multiplication, and division to calculate quantities. You're not going to need to know how to do any complicated quadratic formulas and trigonometry. It's all going to be very, very basic. Welcome to Section 2, the tools and techniques needed for construction quantity takeoffs. So Section 1 laid out the fundamentals. We looked at what quantity takeoffs were and what they're used for, and the general process for how to complete a quantity takeoff. Now, in Section 2, we're going to look more specifically at the tools and techniques you need to master to complete construction quantity takeoffs. We'll talk about different tools available, so both software tools and then just tools for manual measurements, but then also the skills you need to master. So not just math skills, but also construction management skills, time management skills, and even problem solving skills. And then we'll finish off by going through the quantity takeoff tool that I think is the easiest to use, which is Bluebeam. And we'll go through a quick demonstration of how to use Bluebeam and the basic things you need to know about it to complete a quantity takeoff. All right, let's look at the core skills you need to master to effectively complete quantity takeoffs. Intuitively, when you think of a quantity takeoff, you're probably thinking of someone stuck at a desk, reviewing drawings, completing measurements, or using complicated 3D construction softwares. But really, there's a lot more to quantity takeoffs than just measurement. And so there's actually quite a few skills you need to have to be able to effectively complete a quantity takeoff for a construction project. The core skills that we're going to talk about are construction management, understanding engineering documentation, mathematical skills, attention to detail, computer literacy, time management, and also problem solving. While you might not intuitively think of it, you actually need really strong construction management skills to effectively complete a quantity takeoff. Why is this? Because you need to understand what the quantity takeoff is going to be used for. If you don't understand the purpose of the takeoff, you're going to end up producing information that isn't useful. What do I mean by this? Well, if you're doing a quantity takeoff for a conceptual estimate and you spend 3 weeks calculating in detail the quantity of steel reinforcement in a tiny structure, and you've completely wasted all your time and haven't focused on the bigger picture and getting the bigger quantities correct, then you haven't actually contributed to the outcome, which is an accurate conceptual estimate. That's different to if you're completing a quantity takeoff to order steel reinforcement, where you actually need to know in detail the quantities. That's why you need to understand the project outcome you're supporting by doing the quantity takeoff. So you need good construction project management skills, and you need to understand all the different disciplines like estimating, scheduling, procurement, or whatever you're helping to do. On top of that, you need to understand the different construction methods and principles. So for example, if you're doing a quantity takeoff for a concrete wall, then you need to understand the different formwork construction methodologies so you calculate the quantity correctly. Because then you'll need to know whether you need to work out which construction joints you need to measure, the different heights of formwork, what size the panels come in. So you actually need to, in addition to understanding construction project management, you need to understand the different construction methods and methodologies. On top of this, you'll need to understand the different terminologies used. Also, the stages of a construction project. So whether you're completing one in an early stage of a project where it's conceptual and for feasibility, as opposed to a later stage where the quantity takeoff is going to be used in detail for procurement. Next, you need to be able to read and interpret engineering documentation. And this is really a skill in and of itself. There's so many different forms of engineering documentation. You need to be able to read drawings, understand specifications, understanding design principles, and basically what goes into creating the design and the format the design's in. And like I've already spoken about, you're going to need some really, really basic mathematical skills. So you need to be able to, as I've said, add, subtract, multiply, and divide. But nothing more. You're going to also need strong attention to detail. Now, this is a critically important skill when you're talking about quantity takeoffs, because quantity takeoffs require, well, depending what it's used for, require a high level of precision. And we're talking about a high level of precision on likely a boring and repetitive task. So if you're measuring the total volume of concrete you need for a structure, and you're measuring tons of different slabs and walls, there's all these little areas that you could make that cascade, and the end result could be completely wrong if you don't have a high attention to detail, and if you're not carefully checking and making sure that the information that you're using is correct and useful. You also need good computer literacy. So you need to be proficient with basic software tools. Principally, the one you use the most is Microsoft Excel, but also some of the more advanced quantity takeoff tools and softwares. Things like Bluebeam, again, which I'll talk about in a second, is the tool I use. AutoCAD, and if you're working on a project that requires a 3D model, you'll need to be able to use Revitso or Navisworks to interpret the 3D model. The next skill you're going to need is time management. Now, quantity takeoffs can be projects in and of themselves. Measuring all the quantities you need for a massive concrete structure can be a huge exercise. It can take hours or even days to complete. So that's why you need to understand how long different tasks are going to take, what tasks are most critical, and basically manage your own time to complete the quantity takeoff. And it's why it also matters to understand the level of detail and accuracy that you need to produce when you're completing your quantity takeoff. Because if someone's asking you to do a quantity takeoff, but they don't need things to be that accurate, then you don't really want to spend 3 days doing something where you could have got something 80 or 90% as accurate in an hour. So that's why you also need good time management skills to understand how long the task's going to take and what you can realistically produce in the time frame that you've been asked to do it in. And finally, you're going to need good problem solving skills. Whenever you're asked to do a quantity takeoff, there is going to be information missing. Everything you need to do it isn't going to be there. So you're going to have to be able to overcome and resolve these information gaps, and you're going to need to use your own intuition and your own judgment to work out what the best way to complete the quantity takeoff and how to fill in the gaps in the missing information. In summary, quantity takeoffs aren't just about sitting in isolation to complete a detailed review of the drawings and to summarize them in an Excel spreadsheet and send them off. You really need a whole variety of skills to be effective at completing quantity takeoffs. You need good construction management skills. You need to understand the purpose of what the takeoff's for. You need to understand how the project's going to be built. And you need good time management skills. And overall, quantity takeoffs can be quite significant projects in and of themselves. So you're going to need to apply a variety of different skills to effectively complete the quantity takeoff. Now, we're going to talk about quantity takeoff techniques. We're going to discuss what are the very basic techniques that are used to complete a quantity takeoff. The techniques we're going to look at are manual measurement, counting, linear measurement, area measurement, volume measurement, weights, assembly or system estimation, parametric estimation, and software-assisted measurement. Manual measurement is the most basic quantity takeoffs technique and the one you probably think of when you think of what a quantity takeoff is. It's basically taking a ruler and measuring things on a set of drawings. Basically, you take a ruler or a scale, you place it on the drawing, you measure the length on the drawing, and then you multiply it by the scale. So if you measure something on the drawing as 5 centimeters, the scale is 1 to 100, then in real life, the measurement is 5 meters. It's as simple as that. The next is counting. So counting is where you try to measure an individual component and you basically go through all the drawings and count up how much of each of these items there are. So if you're looking at the number of doors, you just go through all the drawings and count the doors, or the number of light fittings and go through all the drawings and count up all of the individual light fittings. The next is linear measurement. So this is where you're measuring quantities that can be summarized as a length. So if we're talking about measuring drainage, conduits, the length of cables or structural beams, and it's just measuring the distance between 2 points. The next are area measurements. So this is where the quantity depends on the surface area. So while the specific formula will vary depending on the shape, typically we're talking about measuring the length and width and multiplying them together if it's a square or rectangular shape. So we're talking about the surface area of a wall, the surface area of a slab, or the amount of painting you need to do. The next is a volume measurement. So volume measurements are where you take length, width, and depth, and that's used for measurements like concrete, the amount of earthworks, or the amount of excavation we need to do. Next, the measuring weights. So this is where we have a set volume and we need to apply a weight per unit of volume. So if we're talking about, for example, measuring how much steel reinforcement we need, that would be measured in tons, or the amount of structural steel we need, or the amount of copper in cables, and that's where we'll generally be taking a volume and multiplying it by the weight per unit of volume. The next system we use is assembly or system estimation, and this is where we estimate the quantities for an entire assembly or system, and then we multiply it by the number of individual systems there are. So for example, if we're trying to work out the amount of formwork consumables we need. Generally, we'll work out the amount of consumables we need per meter squared or maybe per 10 meters squared, and then we'll multiply that by the total meters squared of formwork. Or for example, if we want to know how many electrical consumables we need per distribution board, we'd calculate exactly how we need per one, and then multiply that by the number of distribution boards. Or the amount of mechanical equipment we need for a pump. We work out how much we need for one pump, then we multiply it by the number of pumps on the project. Or if you're working on a solar farm, you need the amount of cable ties you need on one row multiplied by the number of rows for the project. The next quantity takeoff technique we're going to talk about is parametric takeoffs. So this is where rather than counting individual items, we basically take project information from another project and multiply that out by the quantity or parameter for our project. And then this is really used in the early stages of a project where there's incomplete information. So say for example, we want to calculate the key quantities at the very early stages of a solar farm development. And we know that a solar farm that was 10 megawatts had this many trackers. Then if our solar farm is going to be 30 megawatts, then we could times that by 3 to estimate the quantities on our project. Or for example, if we want to calculate the volume of earthworks on a road, and we know a road that was 1 kilometer long had X amount, then if our road's going to be 2 kilometers long, then we simply multiply it by 2. So parametric quantity takeoffs are basically where we find the information from another project and we just adjust it based on a parameter. The final technique is where we do software assisted takeoff. So this is really going to be understanding how to use each individual type of software and then mastering the use of that software and then applying those tools. So we'll talk about how to do that for Bluebeam in this course, but you could use anything. You could use Autodesk, you could use Costex. So it's really just about learning how to use that software with digital drawings to measure all the key quantities. In summary, there are lots of different options we can use to complete a quantity takeoff. So the choice of technique we use is going to depend on the quantity being measured. So for instance, if you're measuring the volume of concrete you need, obviously you're measuring a volume. It's going to be different to measuring the length of drainage, which is a length. It's also going to depend on the available information. So if it's early stages of a project, you might use parametric estimating. If you have an issue for construction drawing set, you're obviously going to be completing detailed measurements. Also depends on the accuracy of the measurement you need. If you just need a high level conceptual figure, then you might just use a parametric estimate. When if you need to complete a detailed bill of quantities, it's going to go into a subcontract and it has to be exactly correct, then you're going to want to do a more detailed measurement. But then also individual preferences impact how you do it. Some people prefer doing things by hand on drawings when other people are much more comfortable using advanced software. And so you're going to get a lot of variance in the choice of technique depending on the person completing the quantity takeoff. Next, let's talk about quantity takeoff tools. We'll look at all the different tools we've got available to us that we can use to complete construction quantity takeoffs. The 3 sets of tools we're going to look at are construction estimating software, building information modeling, and old-fashioned spreadsheets. Construction estimating software consists of these purpose-made softwares for estimating and project management. So these are software systems specifically made for construction estimation. And they're created where you can upload digital drawings. They offer a variety of manual and automatic measuring tools and recording tools. And basically they're set up as simply as possible to take you through the whole quantity takeoff and then estimating process with as little effort as possible. So if we look at some examples of these, we've got Costex, which is a purpose-made estimating software. And then we've got Bluebeam Review, which is the one we'll talk about a bit later on in the course, which is a PDF-based software measurement system. And I think is an incredibly easy way to basically do quantity takeoffs in PDF format. Then we've got PlanSwift, which is a much more basic version of Costex. So if you look at Costex, is more designed for general contractors. PlanSwift is more designed for trade contractors. And then we've got Trimble or Qubit, which is an estimating tool, but specifically made for mechanical and electrical contractors. Then we've got good old-fashioned spreadsheets, probably the most universally applicable construction management tool. And we use that spreadsheet simply for just compiling takeoff data. While they're not purpose-made for estimating or quantity takeoffs, they're still incredibly useful. We just simply record all the information from the takeoff in a single table, and it's easy to sum, add, multiply, and We can basically just set up a range of simple structures for ourselves in Microsoft Excel for collecting our takeoffs. And then finally, we've got building information modeling. So as I've already spoken about, these are 3D digital representations of projects. We can look at all the physical and functional characteristics of a project in a 3D view. And so these are really useful for buildings where we've got a lot of different services and utilities, and it's difficult to make sense of how they work from simply looking at a set of two-dimensional engineering drawings. And these 3D models help us to simplify and automate our takeoffs, and examples of these include Autodesk and Navisworks. With these more advanced softwares, you can get really detailed automated takeoffs, and they can tell you a whole variety of things, like exactly how many service penetrations there are in a slab, the dimensions of pipe, all the different types of pipe used, and the length of pipe. Digital engineering really is the future of construction management, but still, even in 2024, a lot of stuff is just still done by hand on 2D dimensional drawings. So don't be afraid to master the basic quantity takeoff skills. So basically, these are just the most common, simple tools at our disposal to make the basic quantity takeoff process easier. Okay, welcome to section 3. So far we've covered the fundamentals of quantity takeoffs and then the different tools and techniques used to complete a construction quantity takeoff. In section 3, we're going to look specifically at how to complete these takeoffs for all of the different construction activities involved in any major construction project. We'll talk about earthworks, concrete structures, mechanical, electrical and plumbing, and architectural works. Now, for each of these different domains, we'll do a review of the engineering drawings and specifications to understand what we're looking for in the drawings, and then also go through a worked example of how to complete a takeoff using Bluebeam for each of these different types. All right, we're going to start looking at all the different types of quantity takeoffs by looking at earthworks. So earthworks are major civil works. And in this section, we're going to look at how to measure all of the key earthworks quantities. We'll talk about the different types of earthworks drawings and specifications, the basic concepts and definitions you need to understand, and how to measure each of these key quantities. So to start with, we're going to talk about the different earthworks drawings and specifications, and we're going to go through a sample earthworks design package and look at all the typical drawings you'll see and what types of drawings you need to be familiar with. All right, so let's go through a sample set of earthworks drawings. So you can see this project is for some earthworks as part of a golf course, and the project is to construct this new berm along the edge of the golf course as part of flood protection. So like the first drawing is just a general overview and layout of the site. The next drawing, we've got a more detailed drawing that shows the orientation of the berm, and it's also given us these distance markers. So these distance markers are often referred to as chainage markers, and for any longitudinal project, they'll show you what the proposed structure is going to look like at each of these points. And there's also a section view A and a drawing reference, so C317. So if we go to C317, section A, we'll be able to see a cut of the berm that shows the exact design. So we go to this drawing, which is C317, section view A. We've got a typical elevation of the berm. So it shows natural ground level, so existing ground level, then the design for the berm, which shows a 1-in-4 batter with a 10-foot road on top and compacted fill. And then we've also got these diagrams, which were often referred to as cut and fill diagrams, which show a longitudinal section of the berm, or if it's a road, it would be a longitudinal section of the road, and each of these chainage markers, STA 397, refers to a point in the berm. So that's that STA 397. So you could imagine this berm mapped out along these markers. If you're looking at it horizontally, will show you the actual design for the berm. So these diagrams are really useful for working out cut and fill volumes, because we've got our existing ground level as the dashed line, and then the finished level. So we can take difference between these two levels to work out the actual cut and fill volume we need to complete. So just to summarize, we've got our layout or orientation drawing, we've got our profile drawing, and we've got our section view. So if you're talking about earthworks drawings, you're talking about a road, you'd get the exact same three drawings. You'd get a layout of the road, which is useful for orientation and understanding the set out. Then you'll get a profile drawing, which shows existing ground level to finished ground level. And then you'll also get a section view. And you can use these three drawings to calculate all the key quantities you need. And there's also some other drawings showing this sedimentation basin and other elements. But if we're talking simply just understanding earthworks drawings, it's really just this layout or orientation view, this profile view, and this section view. And you can use these three to calculate all the key quantities you need. Next, we're going to talk about some basic earthworks concepts and definitions. So if we're talking about an earthworks quantity takeoff, first thing you need to understand is cut and fill. So you'll hear these two terms thrown around all the time when people talk about earthworks. So cut is another word for excavate. So it's basically the process of removing excavated soil from an area to lower the elevation. And then there's fill. Fill is the opposite of doing a cut. So it's adding soil or rock to a site to raise the elevation to the desired level. So when we talk about earthworks quantities, they'll always talk about cut volumes and fill volumes. The next is swell and shrinkage. So swell is when the soil is excavated, it occupies a larger volume because it's not compacted. So when you dig up soil from the ground, it loses its compaction, so it swells. On the opposite is when you fill material, the volume of the material compresses as it's compacted. So basically it either swells or it shrinks. And then there's standard factors we apply to different materials. So if we're talking about clay, there might be a 15 to 30% swell and shrinkage factor. Silt, there might be 12 to 20%, and sand, there'll be 8 to 15% because the material is more granular. So it compacts and swells less. Next, we're going to look at, on our sample earthworks design package, how to measure these key quantities. The key quantities we're going to need to measure are our volumes, so our cut and fill volumes, so the amount we need to excavate and the amount we need to place. Then we'll also need to look at mass haul diagrams, so these are the distances we need to move the cut and fill material. Topsoil quantities, so if we're talking about new excavation, the amount of topsoil we need to strip, the amount of spoil we're going to need to remove. So this is when there's a difference. Say we're moving the same material from one area to another. If there's an excess that we're excavating over what we're filling, then there's going to be a volume of spoil we need to remove. This is our overburden. And then also we'll look at some trenching and excavation quantity takeoffs. So in summary, earthworks quantity takeoffs are really simple and straightforward. We're basically working out the amount of dirt we need to move from one spot to another. It's basically as simple as that. All right, so now we need to turn this set of drawings into the key earthworks quantities that we can use to schedule and price our project. So the first thing we're going to do is we're going to open an Excel document that is going to be used for our earthworks quantity takeoff. So we'll put earthworks BOQ. Within the table, we're simply going to list out the key quantities we're going to measure. So we're going to clearing and grubbing, so topsoil removal. We're going to note down our cut volume. We'll call it excavation, volume, placement volume. So clearing and grubbing. This is the amount of topsoil we're going to have to remove for our project. And this is actually quite an easy measurement to take. So now, for me, this set of drawings is actually it's hard to use because they're all imperial measurements. But some of you guys are in the US, so you might prefer this, you might find it easier to look at this set of drawings. So all we're going to do to calculate the clearing and grubbing, so this is the amount of topsoil removal, is we're going to look at this typical section view, and Well, then we'll assume that the widths of this berm, we're going to have to make some assumptions around the widths of the berm, and then we're going to be able to get the lengths of the berm from this plan view. And we'll assume we'll have to strip 100 mil of topsoil. So put that down as a comment, 100 mil of topsoil to be stripped. And then what we're going to need to work out is the length of the berm multiplied by the width. And this will give us the area. So if we assume, make a worst case assumption and assume the width of the berm, so if the top road is 10 feet, then we'll assume a 1 in 4 batter. And if the average height of the wall, which they're giving us here, we could take the average of these numbers and work out an average height for the wall and times it by 4, which gives us, because it's a 1 in 4 batter, we know the height of the wall will be 4 times the width. So this is actually another useful tool you can use Bluebeam for, you can go File, Export, Excel Workbook, Page Region, and just select that. And basically, you can just export a table in Bluebeam to a set of measurements. So once that exports, it's given us these numbers. We can just take this average, 8.9 feet. So if our height is 8.9 feet, we can note down, I'll just write this here, average height is 8.9. Then the width is going to be, or I should be more accurate in that description, length of batter, say, was 8.9 times 4, so 35.6. Now, I'm going to convert these to meters, because feet, I find feet confusing, so we go 35.6 feet is 10.85 meters. So now I know the total width of berm is going to be 10.85 plus 2 plus 3. So 3 meters is that road at the top for the golf cart. So if you look at that, we've measured that's on average 11 meters. That's on average 11 meters, and we're allowing 3 meters for the road on the top, which gives us a width. Should I close that? Gives us a width of the berm on average of 24 meters. So then all we need to do to get the clearing and grubbing area is get the total length of the berm, which we don't even need to measure. We can just go off these chainage markers. So if that's 0, to 50, or you can use the scale, which is 1 to 200. So go tools, measure, collie length, and I'll just map out this. Map out this berm. Scale is 1 to 200. And then again, it's given me the unit of length in millimeters, which isn't that useful. I want meters. So it's 128.24 meters. Total width of the berm is 28. I'd actually put in another column. What was it? 128 meters. And the width, 4.7. So a bit. So area. So actually I'll rename that measurement. So our clearing and grubbing is 3,161 meters square. The next is going to be our excavated volume. And so we can look at the profile and we can pretty clearly see that wherever we're looking, the existing ground level is much lower than the top of batter. So there's actually going to be no excavation. So we can mark this as 0 meters cubed. Now we need to calculate our placement volume. So this placement volume is going to be the amount of compacted fill we need to place along this entire profile. The easiest way to calculate that, well, what that is in practice, that's going to be the difference between the top of the berm and the existing ground level. Okay, so the average height between this point and there. We could do this by measuring the average, calculating the average height of the wall the entire way along the profile, or we could just use the data that they've provided us, which they've given the actual height of the wall at each of these separate points, which we already put into, exported to Excel to give us the average height of the wall. Now I actually noticed an error in how Bluebeam exported the data. They didn't have a decimal place between the 7 to the 2, which is why we're getting an average height of the wall of 9 feet, when in practice, it was actually meant to be 3 feet. So it's actually something you have to be careful with in Bluebeam, that sometimes they do miss these little, when you export something directly to Excel, sometimes they'll miss things like little decimal places. So we've got an average height of the wall of 3 feet. So we'll update this to 3, the correct measurement, and we'll get average height in meters is going to be 0.92 meters. Now, what we need to calculate is for this berm, based on an average wall height of 3 meters, what is the area of fill we have to place per meter? I'll just close this quickly. So the way we'll do that is we'll calculate the area of the berm, which is going to be, the berm is going to be made up of 2 triangles and a rectangle. So the area of a triangle is half base by height, so it's going to be 0.5 by the base, which will be the height of the wall, by the length of the batter. It's going to be this times 2 plus this box in here. I think that's how we're approximating the shape of the berm. It's really 1 rectangle and 2 triangles like this. So it's a pretty rough approximation, but in the absence of more accurate survey data and a 3D model, it's probably going to be a pretty accurate approximation. So we get that. That's the triangle. Let's get the rectangle. It's going to be that 10-foot golf cart, which is 3.048 meters by the average height, 2.8. And if we get area, it's going to be 2 times this plus this. So that is the area of berm. So then if we multiply that by the length, we get the placement volume, which is the length by the area, which is 1,636 meters cubed. What we should factor into this is placement for that 100 mil layer of stripping, because remember when we cleared and grubbed 100 mil, we're actually going to lower the natural surface level by 100 mil, so we should factor that in. We're at that volume by the depth, 316 meters cubed. Then we also have to allow that we're going to be placing compacted fill. So we're going to lose some of the volume due to shrinkage when we compact it. So if we allow for a 15% compaction, it will be the sum of these times 0.15. So an additional 200 meters cubed. So total placement will be the sum of these, which gives you 2,200 meters cubed. So what are the key quantities? We've got to strip 3,161 meters squared of topsoil, and we've got to place 2,245 meters cubed of soil. And that's the key quantities we need to complete this Earthworks project. All right, so the final type of civil takeoff we'll look at are trenching takeoffs. So trenching sometimes confuses people, but I think it's by far the easiest way to do the easiest item to do a civil takeoff for. So for example, this is the type of drawing you get for a trench. So this is for high voltage cables. So it shows the power cables, 3 power cables. There's a control cable, communication cable. There's a sand bedding. Then above that, there's a protective cover. So these are sometimes like plastic high voltage cable marker tape that's put above the cables. There's sand and cement, and then there's base course and a road service. So to do a takeoff from this trench, you'd first need to know the length of the trench. So you'd get that from the plan views, which shows you could easily calculate, say it's 100 meters long. And then this is if you can imagine, that's looking down the trench, what it's meant to look at. So you then just simply go and per meter calculate. This drawing doesn't show you enough information to be able to work this out, but if you knew the depth of that, the depth of that, the depth of that, then you just work out per meter how much of the 14:1 sand cement mix you need, how much of the 20:1, how much of the base course. So we assume that, so the depth of the cables is 900 mil. If we can just simply assume that that's 300, that's 300, that's 300. You just break it up into 300 mil sections. Then for your takeoff, you work out how much you need per, call this material per meter. I mean, the other thing, it doesn't show you the width of the trench, but if we assume the width is 0.6 meters, so you need of the 14:1 sand and cement mixture, we'll assume it's got 14:1 cement. Oh, my spelling's off today. Sand/cement. 300 mil depth. Then the volume of that you're going to need is going to be the width times 0.3. So it's 0.18 meters cubed per meter. So that's the metric you use for trenching, meters cubed per meter. For 20:1 sand cement, then it's going to be the same. It's 0.3 deep by 0.6, 0.818 meters cubed per meter. Base course, again, assuming 300 mil depth, 0.18 meters cubed per meter. Then we're also going to need marker tape. And there's 2 separate runs of marker tape. So we're going to use, so per meter, we're going to need 2 meters. And then protective covers, we say it's 200 mil widths. Say it's 3 200 mil widths of cover. We're going to need 3 meters per meter. Then basically, to get what we need for 100 meters, you just times all these numbers by 100. That makes sense, because they're all meters cubed per meter or meters per meter. So for 100 meters of trenching, we're going to need 200 meters of marker tape. For 100 meters of trenching, we're going to need the 14 and 1 sand cement mix. We're going to need a total of 18 meters cubed. And it really is that easy. Trenching, I think, trenching quantities is super easy to work out. You just need the trench profile view and the length of the trench, and that's it. And this same principle can be applied to drainage trenches, electrical trenches, communications trenches, or other utilities. Next, we're going to talk about quantity takeoffs for concrete and steel reinforcement. In this section, we want to understand the key structural concrete quantities. So we're talking about concrete, formwork, steel reinforcement, construction joints, basically all the quantities we need to know to adequately describe a concrete structure. In this section, we're going to talk about concrete drawings and specifications, the key quantities we need to measure, and then go through and do a quantity takeoff of a concrete structure. Let's start by looking at some example concrete drawings and specifications. Alright, so now let's look at some different types of concrete drawings. So out of all the different types of engineering drawings you'll look at, I personally find structures in concrete drawings by far the most confusing. So we're going to quickly go through 3 different sets of drawings. The first is just the simple slab on ground. The second is the abutments for a bridge. And then the third are the footings for a new warehouse. Now they're all sort of slightly the same, but they're all pretty typical structures. So if we look at a slab on ground, what you can see is a profile view of the slab. So if you imagine that's looking in the north-south orientation, there's the slab and then there's beams. So this type of slab is referred to as a raft slab. And then if you look in the east-west orientation, there's horizontal beams running through the slab. What this drawing is showing is that the depth of the slab is 300 mil, and then you can see each of these beams is 650 wide and 800 mil deep. And cast into the slab are these steel plates to support the structural steel, and they're given a detailed cutout of the plate and how it's anchored to the slab. They've also given detail as to the steel reinforcement. So that's just a typical slab on ground. The second one we'll look at is a abutment for a bridge. So if you can imagine, this is at the edge of a bridge, and then this is going to support precast sections that will hold up the bridge deck. So what this is showing us is you've got like an isometric view of the abutments. You can see what the structure is meant to look like. Then you've got a plan view. So if you imagine there's 2 walls or 3 walls, and then a series of plinths on top of the structure, and then a number of piles. So if you look at this, is a plan view where you can see all the different dimensions. And then you've also got a front view at an angle which shows you the heights. So they've given the heights in terms of RLs above ground level, so that's 14.947. The top of the structure is 18.746, 19.052. And then they're also given a section view looking from of the typical headstock. Then the final set of concrete drawings we'll look at, if you can imagine, this is for a new warehouse, and we'll look at the drawings for all of these different footings for the beams. So we go down, here you can see a footing schedule, which shows all the different types of footings and the dimensions. So 2500 by 2000 by 900, that's an F1 footing. Then they've also got details of the steel reinforcement. So 2 layers of SL81 mesh, top and bottom. And then so if we look at the plan view, you can see that's an F1 footing, that's an F3 footing, F3. And they've also given a consistent finished floor, FFL, which is finished floor level at 31.25. That's how all the footings are shown on this drawing. And if we scroll down, they've also given us, this is a jointing plan, so it shows for the actual surface slab. So you can imagine all these footings sit. Just find a section view. You can imagine this is a typical footing detail where you have, so say F1, the footing we were looking at before, there's the footing, and then there's a pavement on top of that. So a slab, 900 deep footing, there's a block out for the column, and then there's this concrete slab on top of that. And this drawing is showing all of the construction joints within the slab. So SCG will be slab construction joint. And this drawing also shows details of the slabs. Okay. So even though this is quite a typical design, quite a simple design, where you've got the different footings in the slab, and then there's just a consistent finished floor level to get the slab. You've also got details of all the joints. Then you've got detailed section views of all the footings. So this is simply denoting that there's steel reinforcement top and bottom, which if you look at the slab schedule, sorry, not the slab schedule, the footing schedule, it tells you all of these, the different types of reinforcements in the footing. The section views, details if you have a service penetration, and it provides all the different section views. So particularly when looking at concrete drawings, you need to pay attention to the general notes. So if you go up to the top of the drawing, there'll generally be a page referred to as the drawing general notes, which are like a guideline for how to interpret the drawings. So we look at what applies to concrete. You can see there's footing notes. So comments on construction sequencing, there's comments on, for example, minimum cover for all the reinforcement. There's comments on the type of concrete testing that's required. There's comments on all the concrete mixes. So this is important to look at when you're looking at noting down the different types of concrete. So you can see the warehouse slab has a different concrete mix strength to the office slab. So that would impact the cost of the concrete you're ordering. And so when you're doing your quantity takeoff, you'll need to note down these measurements separately. There's a comment that, unless otherwise noted, provide N12-400 reinforcement, or up to 450 at splices. So for where this reinforcement detail is not shown properly on the drawings, you'd refer back to the general notes. Comments on the type of concrete testing you need to do. Comments on the specific materials of the concrete. that you need a subfloor vapor barrier. So that's an important thing to note, that while it might not be shown on the drawings, there's a note here to say that there's a subfloor vapor barrier that we'd need to supply and install, that 0.2 millimeters thick. There's comments on the joint sealants. There's comments on construction. So again, referring to a vapor barrier. There's comments on the joints, so construction joints and saw cut joints are to be constructed in accordance with the typical details and installed in the locations shown on the plan. And just lots of comments about the actual construction, slab maintenance. And yeah, just referring to these general notes will make it, they basically make the drawings make sense. They capture all the missing information that isn't shown on the specific plans. Let's look at the key quantities we need to know and need to measure for our concrete structure. When we're doing a quantity takeoff of a concrete structure, the key quantities we're going to need to measure are our blinding, our formwork, our concrete, our construction joints, our reinforcement, and any cast-in items. Blinding is a thin layer of concrete poured when you have a slab on ground to flatten the surface. It's basically a thin layer of concrete poured across the surface area, and it's used to level the surface, it protects the subgrade, and it provides a protective surface area that people can work from. Usually it's between a 30 to 50 mil layer of concrete that gets poured as soon as the earthworks are finished. And this is when we have a slab on ground or any concrete structure that sits directly on the ground. And so it does things like, if it rains, then you don't end up with a whole lot of runoff and pooling, and it basically protects the ground. So when we're doing a blinding takeoff, we really just want to know the areas in meters cubed and then apply this and then get the volume by applying the consistent thickness. So if we have a blinding that's 100 meters squared and it's 50 mil thick, then it's an easy calculation to work out we need 5 meters cubed of blinding. The next quantity we need to know is the quantity of our formwork. So formwork is a temporary mold or casing used when placing concrete. So it's basically when we're pouring concrete, we'll build a either wooden or aluminium frame that we pour the concrete into for the concrete to set. You can have timber formwork, you can have aluminium formwork, or you can have different types of reusable formwork systems. When we're measuring a formwork quantity, we want to get the area of formwork in meters squared. And then from this, we can also get the amount of consumables we need. So for example, if we use X number of consumables in 10 meters squared or 1 meter squared, based on our total amount of formwork, we can calculate the consumables. We also want to make sure we're correctly measuring all the different formwork types. So for example, walls will typically use a different type of formwork to if we're pouring a concrete slab. So you really want to get the individual formwork quantities for each of the different types of structures on the project. Concrete is a mixture of aggregate, cement, and water that forms the material that when we pour it into place hardens over time, and it's really the bedrock of the construction industry. But if you're taking this course, you probably already know what concrete is, so I won't spend too much time explaining it. What we do is we pour concrete into formwork. When we're talking about concrete, the quantity we need to measure is the volume of concrete. So we want to measure the volume of concrete for each individual structure. So we want to look at the different types of structures, so foundations, walls, piers, and beams. Then on our set of drawings, we'll go through and measure the volume of concrete that goes into each of these individual structures. When talking about concrete volumes, it's also really important to understand the construction methodology and the number of pours. The number of pours will be a key driver of the total cost. For example, if we're talking about pouring a 50 meter cube slab, it's very different to having to pour 10 5 meter cube plinths. We'll get completely different production rates. That's why when you're measuring concrete quantities, you want to be sure not just to measure the total volume of concrete in a structure, the number of pours, and the volume of concrete per pour. Joints are deliberate separations between structures. As I was talking about when we're talking about concrete placement, the concrete will be placed in a series of different pours. That's why when we're measuring concrete quantities, we need to understand how all the different slabs are joined. Now, talking about the different types of joints, you've got control or contraction joints. These are set, predetermined joints in the design, which allow when the concrete to set and expand to prevent cracking. Same with expansion joints, that these are set joints in the design that when the concrete pours and set, as it expands or contracts, it will prevent cracking in the slab. Then we've got construction joints. So these are joints that are specifically placed in the not placed in the design, but arise through construction. So for example, if we're pouring a 6 meter high wall, we might pour the wall in 2 different stages, 2 3 meter high pours. At the 3 meter mark, we'll have a set construction joint. These construction joints arise by how the concrete's placed. And then we've also got isolation joints. When we're talking about construction joints, we want to measure the total linear meters of all the different types of joints, because there'll be set materials we need for a joint and then set install and labor rates to apply to the joint. Steel reinforcement is used to be placed inside the concrete structure. Concrete is strong in compression, but not strong in tension. So therefore, steel is placed inside the concrete to make the overall structure stronger. And there's really 2 types of steel reinforcement. We'll get bars or we'll get mesh. So bars are long bars of steel that get fixed into the concrete, and then mesh is where you get pre-made mesh of steel reinforcement that's placed in slabs. When we're talking about steel reinforcement quantities, we're always going to be talking about tons. So how many tons of steel do we need? To calculate the volume in tons, we'll either do a detailed reinforcement takeoff, whereas we individually measure the length of each bar and know the weight per meter of the bar, or we'll simply apply ratios to the volume of concrete. So for example, if we've got 2 meters cubed of concrete, we know that 1 meter cubes of concrete, 1 meter cubes of structural concrete on average has 180 kilos of steel reinforcement. So therefore we can calculate the tons of steel based on the volume of concrete. Now, the level of detail we need to go to and the accuracy of our takeoff will depend whether we just use which measure we use, but overall we want to get the volume of steel in tons. And then when we're talking about steel mesh, we'll get the product type and then also the meters squared of mesh. And then finally, when we're talking about concrete structures, we need to know all the different cast-in items. So these are the items placed within the concrete structure. So examples might include utilities and services. So if we have an electrical conduit that goes through the slab, or if there's hold down bolts, say we're installing a light pole, then we'll have hold down bolts for the light pole that have to get cast into the concrete, or there's a drainage system, a drainage pit lid, and so on and so forth. And for each of these cast in items, we want to know the quantity of that item and the cost. So now we understand all the different quantities we're looking for. Let's go through and do an example quantity takeoff of a concrete structure. The first quantity we're going to measure is the quantity of blinding we need for our slab. Now we'll do it for this warehouse building. So when we were going through the drawings, we saw on the general notes that we need to place a vapor barrier and concrete blinding. Vapor barrier to be installed under the warehouse and office slab. So if we go down to the plan view of the slab with all the footings, to calculate the area of blinding we need, we simply just need the area of the slab. It's as easy as that. We'll just check. So I just Control F on the drawings to see where they refer to blinding, but you can see that there's this thin layer below. Blinding across the length of the slabs, and in the absence them showing a depth, we'll just assume blinding, we'll just assume 50 mil, which is a typical blinding depth. We're also going to need to know the area of the vapor barrier, 0.2 mil vapor barrier on the structure, and to calculate that, all we do is go to the layout view, find out what the scale is, or if there's a scale shown. I actually don't know if there's a scale shown on the drawings. Oh, yes, sorry, there is 1 to 250. That took longer than I anticipated. We just go tool, set scale, custom, 1 centimeter is 2.5 meters. Applied scale, tool, measure, area, and we just go corner, corner, corner. And we also want to include these external slabs. Actually, I've done this wrong because I missed including that pump room. So just quickly bring this out to include the pump room. Like that. And then our area is 13,611 square meters. So that's going to be the area of the vapor barrier in meters squared. And blinding, which will be meters cubed, we just times this area by 0.05 and we get 680 meters cubed of blinding. So for any concrete structure, the next measurement we're going to need to take after we've calculated our blinding is the area of formwork. Now, the formwork is, for the slab on ground, is going to be too simple. So we're going to do the area of formwork we need for this front wall of this bridge abutment. So the way to do that is we first want to look at an overview of this structure and come up with a logical way to break it up. So we'll do it with this lower wall and this rear wall. So if we can imagine and think of this as a sequence of pours, we'd pour this base wall, then as a second pour we'd pour this upper wall, and then we'd pour this series of plinths on top. So that's how you'd pour it. So then we'll break up our formwork takeoff like that. So we've got formwork, and so all our formwork quantities are going to be in meters squared. We've got lower wall, and we'll just put that, the lower wall up to RL 17.149. Then we've got the upper wall, and then we've got plinths. So the lower wall is going to be, and just so we're clear, we're going to exclude these two wing walls because we don't actually have all the heights on the drawings to do this properly. So to calculate that, we're going to need to know the height. So it's going to be the height of this wall, which is 14.239 to 16.45. So go height equals, for those measurements, 16.45 minus 14.239. So it's 2 meters. Length is going to be 22.1 meters. So this is going to give us an area, this length by 2. The reason we've done by 2 is because you think about it, you're going to need formwork on either side of the wall. Then you're also going to need to factor in these stop ends. Makes sense what those are? Those are the ends of the wall. So we're going to need the lengths of these, which they're not actually shown on the drawing. They're given the perpendicular lengths, but not the angled lengths. So we'll just simply go tools, measure length, go from here to here. The custom on the centimeter is 0.5 meters, so that's 150, and then these are 2.2 meters. So the stop ends are going to be, there's 2 of them, they're 2.2 meters long, and they are 2.2 meters high. So then the total formwork we need for the lower wall is going to be the sum of this and this. So 107 meters squared. Now the upper wall. So if you can imagine, that's this upper section of the wall. We know the length, which is this number. The height, which will be 16.45. We'll actually do it. This ends 17.1479 minus to 19.257. So if we go upper wall height is 19.257 minus 17.149, 2 meters. The length we already know. So the area is simply this times 2. Then we also have to factor in the formwork for these stop ends, but remember this wall is only 375mm thick, so it's much thinner than the bottom wall, which was almost 2 meters thick. So if we just allow for that, we get 0.375, area equals 0.375 by 2, because there's 2 stop ends, by the height. So we go equals sum this and this, then it's 9,400. The final thing we need to measure is the plinths. So these are all these structures that bridge beams are going to sit on. They've actually given a naming convention, so BA3, but you've got these girder restraint blocks, BA3, BA1, RA1. So if we simply start off with listing out all these different types, so we've got 2 girder restraint blocks. Break these out here. So you got girder restraint. Number 2. Then BA3, there's 1, 2 BA3. BA1 is 1, 2, 3, 4. BA2 is 1, 2, 3. And then RA1, there's 1, 2, and RA1 is 2. So For each of these, then we're going to need the individual dimensions of the blocks. So we just break this out into length, width, height, and we quickly go and calculate these. So measure, so this one is 520 by 1.3 to BA3 is 1.9 by 0.95. BA1 is 0.79 by 0.95. BA2 1.5 by 0.95. 5. It's at 1.9. Oh, sorry, 1.5, not 1.95. More like 1.45. And then RA1 is 0.78 by 0.8. And 8 by 0.8. And then we simply just get the heights. 1.15. And I'm just going to take the worst case heights when they're on the slope. 0.35. And the change that, that's BA1, 0.275. So BA2 0.26. So, and then RA1 is 1.039. Now, to get the area of formwork we need is going to simply be the height times 2 by the length plus 2 by the width times the number. So that's the perimeter formwork, each of these. Drag that down. And then we can simply get 26 meters squared. Now, these are the actual quantities of formwork. If we wanted, we could put in some reasonable wastage. However, depending on your preference, you could be double counting if you're doing this, because estimators will typically do this as well. So there we got 251 meters squared of formwork. All right, so the next quantity we're going to do is the quantity of concrete we need. And we'll do it for this bridge abutment, excluding the wing walls, because we've already taken all the measurements, so this should be really quick to do. So volume of concrete, and this is going to be in meters cubed. So we typically will do the same breakdown. We'll do the lower wall, the upper wall, and the plinths, and that's going to reflect our pour sequence as well. So if we go the lower wall, all we need to know is the height, the length. Take these two measurements and our volume, height, length, and depth. And our depth was 2.2. So then our volume is just simply going to be the height by the length by the depth. 107 meters cubed. The upper wall, we get the same measurements. The volume of concrete was, the depth was 0.365. The volumes simply get to be the height by the length by the depth. Then for the plinths, just copy this whole thing across. It's gonna be the length by the width by the height by the number. And we just sum these together. There you go, and there's our volumes of concrete for each structure. Alright, so now we've got our blinding area, our formwork, and our concrete. We need to know our steel reinforcement. So steel reinforcement is going to be a quantity in tons. When people talk about steel fixing, they always talk about tons of steel. So with a drawing like this, we don't have any steel details, so we couldn't do a proper steel reinforcement takeoff. But the easiest way to do it, the standard way of doing it, would just be to assume something like 140 kilograms of steel per meter cubed of concrete. Now that's just the standard measurement you can use. You can look up online, and there's you can use different ratios. So there'll be different ratios of concrete to steel depending on the structure type, but that information is really easy to find online. So if we then go total volume of concrete, which we know is the sum of those, so total volume, 131 meters cubed, pool 31 meters cubed, and we can just convert this to tons of steel by 131 meters cubed by 0.14, and we get 18 tons of steel. The other way we can calculate our tons of steel is the detailed way. This is where we look at the actual steel fixing details of a slab. So for example, this footing, F1, has 2 layers of SL81 mesh, top and bottom. Then we can find the actual weight per unit of measure. So if you're talking about bars, it would be the weight of steel per bar. Or if you're talking about mesh, it'd be the weight per meter squared. So I just simply found this information online that says typical SL81 is 105 kilograms per unit of measure. They've said a standard unit of measure is 6 meter by 2.4 meter sheet. So we say SL81 mesh is 0.105 tons, and that is for the area of 6 by 2.4. So then we can convert this to per meter squared. The weight in tons per meter squared is that. The weight per meter squared is 0.007 tons. So for then our footing F1, there's 2 layers of SL81 mesh, 1 layer at the top, 1 layer at the bottom. The dimensions of the footing are 2500 by 200. So then we get area. The F1 footing would be 2 by 2.5. There's 2 layers. So total mesh, we times that by 2 because there's a layer on the top and a layer on the bottom. Meter squared. And the weight of steel for that F1 footing would be that amount by that, 0.07 tons. Now that's the detailed way of doing it. That works for both mesh and bars. So for bars, we'd need the weight of the bar per meter. So say we have a drawing that shows a bar in it, for example, 4N12 R10 leagues. So this is a detailed of a step down and a strip footing. So if we want to measure 2, we'd get the weight of an N12 bar per meter. So that's a 12 mil steel bar. So we Google 4N12 bar per meter. And the reason I'm saying to Google this stuff is because it's all available online. So if we look at these deformed bars, we can see mass per meter, so kilograms per meter, and 12 and 16.9278 kilograms per meter. And what was ours? Ours is N12, so we can simply take this N12.9278, so N12.9278 kilograms per meter, and say if we measure in the strip footing, that say it's a 350 mil step and that's a 300 mil slab, and these bars are at 300 spacing, and we want to measure the length across 10, how much steel you need for 10 meters of this step down footing. So 2 bars, so length we said is 300 mil step plus 300 mil slab, so 0.6, so equals 0.6, so I'll call that height. The length, we'll say we'll measure it for 10 meters, so we'll do weight per meter, and you get, so you've got two bars, so 1.2 meters per meter by the weight, 1 kilogram, and then it's across 10 meters, so you get 11 kilograms, and then the weight in tons is going to be that divided by 1,000. And it's easy as that. So we've got two-way, we can assume a weight per kilogram per meters cubed, or we could do a detailed calculation where we work out the total meters squared of mesh, or we've called a mesh, mesh, the total meters squared of mesh by the weight per meter squared, or the length of bars by the weight per meter of bar. All right, so the final quantity we need when we're talking about a concrete structure is the length of the joints. So you can see on this, so what you want to find is the jointing plan. We've got one here, and this is showing different types of joints. So DCG is a doweled construction joint. SCCG is a sawn construction joint. So we actually want to break down our measurements into our SCG, our sawn construction joints, and our doweled construction joints. So we add a new tab to our workbook, which is joints. We want saw cut joints and doweled joints. And simply all we're going to do for these is we take the scale on the drawing, wherever that is, and then we just have to measure the lengths of all of the individual joints. The scales of 1 to 250. All I'd do here is I'd measure what's the outer length of the warehouse. Go to set the scale again. So 1 centimeter is 2.5 meters. So it's 84 meters.
They're right to that. I don't quit. And they think they could do it.
So it's 84 meters by 157 meters. And then I'll just work out big. So the length is 84 meters. The width was 157 meters. I'd go number horizontal, number vertical. Just call that vertical, and the width as horizontal. The number of horizontal vertical saw cut joints is computer keeps freezing. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. Number of horizontal is 1, 2, 3, 4, 5, 6. And I'm oversimplifying this because I'm just ignoring the office area and I'm ignoring these other two slabs, but the principle is the same. You can do it in more detail if you need to get an accurate takeoff. And then, so that's for the saw cut joints. For the dowel, we've got 1, 2, 3, 4 horizontal ones. That's right, that was vertical. There's 4 vertical. And how many horizontal joints are there? There's 1, there's 2. And then to convert this to length, we just go the vertical by the length plus the number of horizontal. So it gives us 1698 meters of saw cut joints, and then for horizontal, vertical, and 650 meters of dowel joints. In this section, we're going to look at architectural quantity takeoff. So if we're talking buildings, we're talking walls, facades, floors, ceilings, these sorts of architectural elements of a project. So if you're exclusively working on heavy civil projects like roads or bridges or tunnels, architectural quantity takeoffs aren't going to be super relevant. However, if you're working on a building project, this section will probably be the most relevant to the type of work you're going to be supervising and managing. In this section, we're going to look at how to understand architectural drawings, the key quantities you'll need to be measuring, and then we'll go through a worked example of how to measure all of these key quantities. Let's start by understanding architectural drawings. Alright, so looking at a set of architectural drawings, we want to try and find the different wall types, the different floor types, the number of windows and the number of doors. And this is all pretty standard things that you'd be familiar with on most projects, but basically, for each of these different types of drawings, you want to find a drawing that has architectural typicals on it, like this drawing, which shows some typical internal doors and floors. And there are layout drawings, like this one, for example, which denotes all of the different so floor types. And then you can see up in the notes the different floor types it refers to. So F1 is a floor hardener finished with smooth and polished, and then F1 is the concrete floor in the cupboard, and then the different wall types. So W1 refers to garage painting over the blocks with a water-based primer, and then W2 is bathroom rendering with ceramic tiles. Then we've got roofs as well. So R2 is the inside ceiling of plasterboard. And basically the different details, there's a fence detail, which has a fixed fence and a sliding fence. But basically architectural drawings refer to all the different types of fixtures and finishes used on the project. And they've also got the external floors outside. And then external facades. So the architectural drawings will basically show plan layouts of the building and all of the different types of fixtures and finishes, the roofing detail. So the type of roof used, the box gutter, and they'll show all these extensive details and all the different wall types and plan sections of the buildings. Now, let's look at the key quantities you'll need to be going through the drawings and working out how to measure. The key architectural quantities you'll need to be looking at are walls, furnishings, fixtures and equipment, windows and doors, and different surface finishes. So, walls. When we're talking about walls, we need to know the different types of walls that are used. So, for example, whether they're a load-bearing structural wall or an internal wall. And then also, generally, we'll measure the area in meters squared of a wall. And also, we'll need to factor in any openings, so doors or windows within the wall. When we're talking about furnishings, we're looking at the quantity and different types of furnishings. So we'll look at things like cabinets, countertops, and seating. And then generally, we'll just perform a count measurement for all of the different items that we're taking. In some instances, though, size will play a role. For example, for built-in cupboards, we might need to know the volume of the cupboard. Or for countertops, we might need to know the length of countertops. But generally for furnishings, it'll just simply be a count measurement. Next, we've got fixtures and equipment. Now, generally when we're talking fixtures and equipment, this will come under the services drawings. So the mechanical, electrical, and plumbing drawings. And count things like the number of light fittings, the number of fire extinguishers, or the number of light switches. Now, we'll also cover these under mechanical, electrical, and plumbing, but in some instances, you can have fixtures and equipment that fall outside of the MEP takeoffs. So in those instances, we'll need to capture them under our architectural takeoff. Next, we've got windows and doors. So windows and doors will be the quantity and the type, and it will simply just be same with the other types, just the count measurement on the drawings. We'll go through, count up all the different types of doors and categorize them by their different size and openings. Then we've got finishes. So finishes are things like painting, tiling, carpet. And for all of these different types of finishes, we'll be categorizing the types and the quantities. So for example, we'll need to know the meters squared of carpet, the meters squared of painting, or the meters squared of tiling. And here it's important to distinguish between the different trades as well. So for example, under plumbing, we might have tiling might be captured under the plumbing takeoff, because it's a wet area, but not necessarily. And that's why it's important to distinguish between what's going to fall under the services scope and what's going to fall under the architectural scope. So now we've gone through the key quantities we're going to be measuring. We're going to go through a worked example of how to actually measure these quantities. So now we're going to complete our quantity takeoff for the architectural work. We're going to be working out the area of the walls, the amount of floor treatment we have to provide, the different doors and windows, and any of the furnishings within the building. So we'll start off with just setting up a spreadsheet that we're going to record this information. So we'll set up the items. So there'll be the walls, the painting of the walls. Remember the structure, for this structure, there's a series of internal walls that are all blockwork masonry walls that get different painting. And within the bathroom, they get tiled. If you want to look at that information, there's along the general notes on the side of the drawing, you can see the different floor treatments. So F2, F1, F0, and then the different wall types. And there's a drawing that clearly you can see that there's 3 different types of walls looking along the different axes of the building. So 3 different heights of walls looking along the axis of the building. And there's several doors and windows within them. See windows along the top. You can see there's the different floor types, the different wall types, and then there's ceiling plasterboard. So to begin with, yes, this drawing shows that within the bathroom there's a tiled wall, wall 2, wall 1. So if you're looking at a set of plans like this, it can get a bit confusing looking at all the different axes and the angles we're looking at. And that's why you're increasingly seeing for building projects the use of 3D models, because it just makes it easier to understand which angle you're looking at and which quantity you're taking. So let's start off with the lengths of the walls. So first we'll look at the different heights of the walls. So remember, if we're looking from this angle, that is actually a window. So if we find that drawing, that there's a window along the top there. So there's, in the north-south axis, we've got 3 separate wall heights. We've got, I'll just write this down. So north axis, there's axis A, axis B, say axis B, axis C. We'll just call this axes. Axis A, the wall's 3216. Axis B, it is 3623. And there's that 1815 window at the top. And same with axis C. You get the lengths of those as well. And then in the in the east-west direction, there's wall on axis 1 and axis 2 and axis 5. So axis 1, axis 2, axis 5. So along axis 1, got to work out the height of that wall. I need to find a good drawing. Oh yeah, that's that pentagram shape. So that, if you imagine that, that is that axis. It's probably not really, you'd have to break that into 2 separate sections, that wall. And then along axis 2, which is that internal wall. Again, that'll be the same shape. And then the garage door is in that axis 1, if you can picture that. That's that shape. That's that section. So to get the area of these walls, we will, just get the lengths of the north-south, so axis A, it's going to be 1159 plus 3188. 14 meters. Axis B, there is only 2 small sections of wall. That's a mistake. That should be C. There's a mistake on the drawings. And then axis B will also be, and to get area, we just go multiply that by that. That's going to give us the area of wall in meters squared. Along axis 1, so this axis, we're actually going to need to do a calculation. So you can represent this shape as a square and a triangle. And then we'll also need to make an approximation for this shape with a square and the triangle. Or we can make things easier for ourselves and just use the area function on Bluebeam. We'll just start off, just have to set the scale. Is that 6.95? Then I get tool measured as area. You just get the measure in the area of this entire face. 41.41 square meters. And axis 2, it's going to be the same. And here we're double counting the door penetrations, if you think about it, because there's a door there, but it's such a small opening, we'll probably just leave it in. The garage door, however, we'll just take that area. Actually, that is a different wall type though. We'll just take that area. To the 6 square meters. And that is 6.5. It was 6 plus 6.5. So we've got a total area. It's going to be the sum of that, 200 meters squared. So next, we've got to work out the treatments of the walls. So there's painting over the blocks with wall-based primer. So that's going to be the majority of the walls. And then in the bathrooms, there's bathroom rendering with ceramic tiles. So we've got the total area of walls. Then we'll get the area of painting and the area of ceramic tiles. So you get the area of painting. It's going to be either side of the blocks, if you imagine that. So it'll be twice the area of the walls minus whatever we're doing on the tiling. So if I go down to the bathroom drawings, you can see, you can imagine that. Along 4 sides of the walls, we'll have this ceramic tiles, and you just need to measure that area. However, they don't seem to have given a scale on the set of drawings for the ceramic tiles. Which is unfortunate, but we do have the height of these windows. If you look at, okay, that's the measurement I was looking for. Your 1790 is the height of the window. And you can see on this drawing, the underside of the tiles roughly aligns with the height of the window. Now, this isn't going to be exact, but going to make the best we can do with missing information. So just call this 100 mil higher than the height of the windows. We'll say the height of this is 1890. And then the length of these tiles is going to be the perimeter of this bathroom room. It's going to be 3880 times 2 plus 2000 times 2. So we go 1.89 is the height by 3.88 by 2 plus 2 by 2. And that gives you 22.24 meters squared. It's going to be the indoor ceramic tiles. And so the area of painting is going to be total area of the walls times 2, because you have to paint both sides of the walls, minus the area we're tiling. It's 279 meters squared. The next thing we want to work out is our floors. So if we look at the different floor types, we've got the bathroom surface, and then just the simple floor hardener, finished floor hardener applied to the garage. So this is going to be pretty simple to work out. So I'll just calibrate the scale for this drawing. But 7.2 meters, and then I'll just go. So for the treated concrete, just get this area. It's 124 square meters, and for the bathroom flooring, 6.7. What was that? That was 124. And then finally, we just want to work out the numbers of doors and windows we're going to need. So if we look at this drawing along, well, probably we'll just go to the plan view first, but you can see at the south entrance, there's a garage door. And then we've got these two internal doors and the external door. So if we just start off with doors, there's the garage door. There's the we'll call this door 1. So 1300 mil external door, door 2, 1700 mil internal door, and door 3 is the 800 mil bathroom door. The windows, we've got no windows on the north-south facades, so the east-west or the south facades. On the north facade, we've got these 4 upper windows, so we'll call them the upper windows, 4 upper windows, and then the smaller bathroom window And then the way I'm structuring this isn't very organized or messy or sophisticated, but it's all you need. And then we've got this 1450 by 26 window. And 1607 by 1624 window. And as you can see, from the drawings, we worked out our total masonry wall area. So blockwork wall, 200 meters squared. We've got our painting, our area of ceramic tiles, the area of treated concrete, and the area of bathroom flooring. We've worked out our doors. We've worked out our windows. And so these are the key architectural quantities that we need to then price or schedule our job. In this section, we're going to look at architectural quantity takeoff. So if we're talking buildings, we're talking walls, facades, floors, ceilings, these sorts of architectural elements of a project. So if you're exclusively working on heavy civil projects like roads or bridges or tunnels, architectural quantity takeoffs aren't going to be super relevant. However, if you're working on a building project, this section will probably be the most relevant to the type of work you're going to be supervising and managing. In this section, we're going to look at how to understand architectural drawings, the key quantities you'll need to be measuring, and then we'll go through a worked example of how to measure all of these key quantities. Let's start by understanding architectural drawings. All right, so looking at a set of architectural drawings, we want to try and find the different wall types, the different floor types, the number of windows and the number of doors. And this is all pretty standard things that you'd be familiar with on most projects. But basically, for each of these different types of drawings, you want to find a drawing that has architectural typicals on it, like this drawing, which shows some typical internal doors and floors. And there are layout drawings like this one, for example, which denotes all of the different so floor types. And then we can see up in the notes the different floor types it refers to. So F1 is a floor hardener finished with smooth and polished. And then F1 is the concrete floor in the cupboard. And then the different wall types. So W1 refers to garage painting over the blocks with a water-based primer. And then W2 is bathroom rendering with ceramic tiles. Then we've got roofs as well. So R2 is the inside ceiling of plasterboard. And basically the different details, there's a fence detail, which has a fixed fence and a sliding fence. But basically architectural drawings refer to all the different types of fixtures and finishes used on the project. And they've also got the external floors outside. And then external facades. So the architectural drawings will basically show plan layouts of the building and all the different types of fixtures and finishes, the roofing detail. So the type of roof used, the box gutter, and they'll show all these extensive details and all the different wall types and plan sections of the buildings. Now, let's look at the key quantities you'll need to be going through the drawings and working out how to measure. The key architectural quantities you'll need to be looking at are walls, furnishings, fixtures and equipment, windows and doors, and different surface finishes. So, walls. When we're talking about walls, we need to know the different types of walls that are used. So, for example, whether they're a load-bearing structural wall or an internal wall. And then also, generally, we'll measure the area in meters squared of a wall. And also, we'll need to factor in any openings, so doors or windows within the wall. When we're talking about furnishings, we're looking at the quantity and different types of furnishings. So we'll look at things like cabinets, countertops, and seating. And then generally we'll just perform a count measurement for all of the different items that we're taking. In some instances though, size will play a role. For example, for built-in cupboards, we might need to know the volume of the cupboard. Or for countertops, we might need to know the length of countertops. But generally for furnishings, it'll just simply be a count measurement. Next, we've got fixtures and equipment. Now, generally when we're talking fixtures and equipment, this will come under the services drawings. So the mechanical, electrical, and plumbing drawings. And count things like the number of light fittings, the number of fire extinguishers, or the number of light switches. Now, we'll also cover these under mechanical, electrical, and plumbing, but in some instances you can have fixtures and equipment that fall outside of the MEP takeoffs. So in those instances, we'll need to capture them under our architectural takeoff. Next, we've got windows and doors. So windows and doors will be the quantity and the type, and it will simply just be same with the other types, just the count measurement on the drawings. We'll go through, count up all the different types of doors and categorize them by their different size and openings. Then we've got finishes. So finishes are things like painting, tiling, carpet, and for all of these different types of finishes, we'll be categorizing the types and the quantities. So for example, we'll need to know the meters squared of carpet, the meters squared of painting, or the meters squared of tiling. And here it's important to distinguish between the different trades as well. So for example, under plumbing, we might have tiling might be captured under the plumbing takeoff, but because it's a wet area, but not necessarily. And that's why it's important to distinguish between what's going to fall under the services scope and what's going to fall under the architectural scope. So now we've gone through the key quantities we're going to be measuring. We're going to go through a worked example of how to actually measure these quantities. So now we're going to complete our quantity takeoff for the architectural work. We're going to be working out the area of the walls, the amount of floor treatment we have to provide, the different doors and windows, and any of the furnishings within the building. So we'll start off with just setting up a spreadsheet that we're going to record this information. So we'll list out the items. So there'll be the walls, the painting of the walls. Remember the structure, for this structure, there's a series of internal walls that are all blockwork masonry walls that get different painting. And within the bathroom, they get tiled. If you want to look at that information, there's along the general notes on the side of the drawing, you can see the different floor treatments. So F2, F1, F0. And then the different wall types. And there's a drawing that clearly you can see that there's 3 different types of walls looking along the different axes of the building. So 3 different heights of walls looking along the axis of the building. And there's several doors and windows within them. See windows along the top. You can see there's the different floor types, the different wall types, and then there's ceiling plasterboard. So to begin with, yes, this drawing shows that within the bathroom there's a tiled wall, wall 2, wall 1. So if you're looking at a set of plans like this, it can get a bit confusing looking at all the different axes and the angles we're looking at. And that's why you're increasingly seeing for building projects the use of 3D models, because it just makes it easier to understand which angle you're looking at and which quantity you're taking. So let's start off with the lengths of the walls. So first we'll look at the different heights of the walls. So remember, if we're looking from this angle, that is actually a window. So if we find that drawing, that there's a window along the top there. So there's in the north-south axis, we've got 3 separate wall heights. We've got, I'll just write this down. So north axis, there's axis A, axis B, say axis B, axis C. We'll just call this axes. Axis A, the wall's 3216. Axis B, it is 3623. And there's that 1815 window at the top. And same with axis C. You get the lengths of those as well. And then in the in the east-west direction, there's wall on axis 1, and axis 2, and axis 5. So axis 1, axis 2, axis 5. So along axis 1, got to work out the height of that wall. I need to find a good drawing. Oh yeah, that's that pentagram shape. So that, if you imagine that, that is that axis. It's probably not really, you'd have to break that into two separate sections, that wall. And then along axis 2, which is that internal wall. Again, that'll be the same shape. And then the garage door is in axis, that axis 1, if you can picture that. That's that shape. That's that section. So, to get the area of these walls, we will, so just get the lengths of the north-south, so axis A, it's going to be 1159 plus 3.88. 14 meters. Axis B, there is only 2 small sections of wall. That's a mistake, that should be C. There's a mistake on the drawings. And then axis B will also be, and to get area, we just go multiply that by that. That's going to give us the area of wall in meters squared. Along axis 1, so this axis, we're actually going to need to do a calculation. So you can represent this shape as a square and a triangle. And then we'll also need to make an approximation for this shape with a square and a triangle. Or we can make things easier for ourselves and just use the area function on Bluebeam. We'll just start off, just have to set the scale. Is that 6.95? And then get tool, measure this area. You just get the measure in the area of this entire face. 41.41 square meters. And axis 2, it's going to be the same. And here we're double counting the door penetrations, if you think about it, because there's a door there, but it's such a small opening, we'll probably just leave it in. The garage door, however, we'll just take that area. Actually, that is a different wall type though. We'll just take that area. To 6 square meters. And that is 6.5. It was 6 plus 6.5. So we've got a total area. It's going to be some that 200 meters squared. So next we've got to work out the treatments of the walls. So there's painting over the blocks, the wall-based primer. So that's going to be the majority of the walls. And then in the bathrooms, there's bathroom rendering with ceramic tiles. So we've got the total area of walls. Then we'll get the area of painting and the area of ceramic tiles. So you get the area of painting, it's going to be either side of the blocks, if you imagine that. So it'll be twice the area of the walls minus whatever we're doing on the tiling. So if I go down to the bathroom drawings, you can see, you can imagine that. Along 4 sides of the walls, we'll have this ceramic tiles, and you just need to measure that area. However, they don't seem to have given a scale on the set of drawings for the ceramic tiles. Which is unfortunate, but we do have the height of these windows. If you look at, okay, that's the measurement I was looking for. Your 1790 is the height of the window. And you can see on this drawing, the underside of the tiles roughly aligns with the height of the window. Now, this isn't going to be exact, but going to make the best we can do with missing information. So just call this 100 mil higher than the height of the windows. We'll say the height of this is 1890. And then the length of these tiles is going to be the perimeter of this bathroom room. It's going to be 3880 times 2 plus 2000 times 2. So we go 1.89 is the height by 3.88 by by 2 plus 2 by 2. And that gives you 22.24 meters squared. It's going to be the indoor ceramic tiles. And so the area of painting is going to be total area of the walls times 2, because you have to paint both sides of the walls, minus the area we're tiling. It's 279 meters squared. The next thing we want to work out is our floors. So if we look at the different floor types, we've got the bathroom surface, and then just the simple floor hardener, finished floor hardener applied to the garage. So this is going to be pretty simple to work out. So I'll just calibrate the scale for this drawing. But 7.2 meters, and then I'll just go. So for the treated concrete, just get this area. It's 124 square meters, and for the bathroom flooring, 6.7. What was that? That was 124. And then finally, we just want to work out the numbers of doors and windows we're going to need. So if we look at this drawing, we'll just go to the plan view first. But you can see at the south entrance, there's a garage door. And then we've got these two internal doors and the external door. So if we just start off with doors, there's the garage door. There's the we'll call this door 1. So 1300 mil external door. Door 2. 1700 mil internal door. And door 3 is the 800 mil bathroom door. The windows, we've got no windows on the north-south facades, so the east-west or the south facades. On the north facade, we've got these 4 upper windows, so we'll call them the upper windows, 4 upper windows, and then the smaller bathroom window. And then the way I'm structuring this isn't very organized or messy or sophisticated, but it's all you need. And then we've got this 1450 by 26 window. And 1607 by 1624 window. And as you can see, from the drawings, we worked out our total masonry wall area. So blockwork wall, 200 meters squared. We've got our painting, our area of ceramic tiles, the area of treated concrete, and the area of bathroom flooring. We've worked out our doors. We've worked out our windows. And so these are the key architectural quantities that we need to then price or schedule our job. Now, let's look at mechanical, electrical, and plumbing takeoffs. Now, for a lot of you civil engineers out there, this is probably going to be the most confusing section because you're not familiar with looking at mechanical drawings, electrical drawings, or hydraulic drawings. But it's much simpler than you're probably originally thinking, so don't stress too much. Just basically, we'll go through, understand the different types of drawings, what's shown on the drawings, and then we'll look at the key quantities that you need to be able to measure. So in this section on MEP takeoffs, we're going to talk about the different MEP drawings and specifications, the different types of quantities you'll be measuring, and like with the other sections, we'll go through a worked example of how to measure these key quantities. Let's start with looking at an example drawing package of mechanical, electrical, and plumbing, and we'll go through all the different types of drawings and what they're representing and what they're showing. All right. Now we're going to look at some example mechanical, electrical, and plumbing drawings. And you'll notice when looking at these sorts of drawings, whether they're mechanical, whether they're electrical, they come in two categories. You've got schematics and you've got layouts. So what a schematic tells us is basically how everything's connected. They're like a wiring diagram. So this really, really simple example shows the incoming supply from the street, the house distribution panel, and then the services that are connected to the distribution panel. So there's the lighting, the hot water, the washing machine and hot water, the plugs, and the kitchen. Now, this is just a really, really basic example of a single electrical single line diagram of a schematic. Then as well, you'll need to read this information in parallel with a layout drawing. Now, what a layout drawing tells you is physically where everything is. So this is an example of an electrical layout that shows you where the lights are, the recessed lights, the wall mounted lights, where the fan is, and the power outlets. And there's also data cabling for a telephone outlet and the switches. So when we're talking about electrical drawings, there'll be a schematic that shows you the interconnection of all the services, and there'll be a layout. Same with a plumbing drawing. So this is an example plumbing schematic for, this is more complicated than a simple house or building, but there's a chiller, a membrane, an air vacuum. But basically, even if we don't understand what all this stuff does, they're all separate pieces of equipment, and this diagram is showing how they're interconnected. Then we've got our plumbing layout that shows where the pipes run, the different colors of the pipes would represent the different services. So red would be hot water, blue would be drinking water, and purple would be drainage. We just look really simply, just tells us where everything is and where everything connects. And then same with the mechanical. We've got a schematic drawing that shows how everything's connected. And then we've just got a simple layout drawing that shows the actual position of ducts, of the fans, and where the ventilation points are. So for our sample set of design drawings, let's look at how the services information is shown for our example garage project. We've got, firstly, if we look at the architectural layouts, you can see there's a water tank slab with a rainwater tank. There's a bathroom, so there's obviously going to be water running to the bathroom. And then within the indoor areas, we're obviously going to need lighting and power. So if we look, this is the electrical drawing. You can see that the schematic information is represented as a table. So it shows the information about the distribution board, the information about the different circuits, and then it also shows on each circuit what services are connected. So each of these represents a light, each of these represents a power point. And then if we look at this, we've got an internal building layout and an external building layout. So this is the power to there's a electric gate. So this is the power to the gate and the earthing. this shows as well that the incoming, that's the power to the gate motor, that's the meter and the street supply and the earthing point to the grid electric supply, the distribution board, and on the layout drawing you can see electric, you can see what an underground duct, there's roofing duct, and there's duct for the electric door. So basically, if you look at this layout diagram, you can see the position of all the lights and the sockets, and then how they all connect back to the distribution board. So you can see these are connected by an underground duct, these are connected by a roof duct, and then there's an underground duct out to the rainwater tank pump. It also just shows you, if you go back, you can see which circuit these sit on in the distribution board. So if we think of this as a schematic, while this isn't represented as a single line diagram, you could imagine that each of these represents a circuit and it shows all the services connected to it, but it's just represented in a table rather than a single line diagram. Now, if we go to find our hydraulics drawings, for example, this is an internal layout of the building. It shows the different valve types, the connections to the shower, the different services running. So you can see the actual pipework. So green represents rainwater, so drainage from the pipes. Pink represents the sewer, and blue represents the drinkable water. So if we find, there's another layout drawing that shows the sewage. So there's a floor drain, connection to the pipe, and external layout. So you can see the metering point from the street, the connection of the drinking water. Pink represents the sewer, and then we've also got the rainwater drainage to the street, the connections from the roof. So there'd be roof plumbing in a box gutter and collects the water that runs to the tanks. So you can see in these drawings that you've just got a simple layout that shows the orientation and position of where everything is, the different types of water services, and how all the drainage is connected. Now we've understood how to read mechanical, electrical, and plumbing drawings, let's now look at what are the key quantities you're going to need to measure to accurately estimate, schedule, or procure. We'll look at each of these key quantities based on the different trades. So we'll look at mechanical systems, electrical systems, plumbing systems, and then also fire protection systems. So fire protection systems generally sometimes fall under plumbing, but they are a big part of any building project. For mechanical systems, our key quantities will be our ductwork, our HVAC units, and any room fittings. And so for any ductwork and pipes, we'll use linear measurement. So we'll simply measure how long they are, all the different types of ductwork and sizes. And then for the fixtures and HVAC units, we'll do a count measurement. So we'll simply count up how many of each of the different types there are. And then we'll also note down all of the different material types and specifications, so we correctly categorize our measurements and our counts. Electrical systems, we want to know the length of wiring, conduits, the number of outlets, the number of switches, and the number of light fixtures. And so same with the mechanical, for any of our cabling and conduits, we'll need to perform a linear measurement of all the different types and sizes. And then for our light fittings and outlets and distribution boards, will simply perform a count measurement. It's also important to consider data cabling versus electrical cabling, and also the different sizes and types of distribution boards and panels. But that should all be shown clearly in the drawings and specifications. For our plumbing systems, we'll need to know the different length of pipes, the number of fittings, the number of fixtures, and so things like sinks, toilets, and showers, and also hot water units. And we need to consider the different types of services. So plumbing, there's obviously potable water, which is drinkable water, there's drainage, there's sewerage, there's hot water. So we need to consider all these different types of plumbing services, and same with the mechanical and electrical. For any pipe work, we'll just simply perform a linear measurement to record the different quantities and types. And then for our fixtures, we'll perform a count measurement. And finally, for our fire protection, we'll need to count the number of sprinkler heads, the length of piping, the number of valves, the number of fire extinguishers and the number of alarms. And we should consider that any of the fire systems will be broken down into either the wet fire, which is the reticulation of the sprinklers, or any dry fire, which is things like fire alarms or fire extinguishers. And same with the others, we'll perform a linear measurement for all the piping and plumbing, and then simply a count measurement for any of the fixtures. Now, let's go on to our worked example of measuring all of these key quantities. To complete our quantity takeoff, we'll review the electrical drawings and the plumbing drawings, and we want to measure all of the key quantities. We just open an Excel document to set this up. We'll say for electrical, we want distribution board, want the light fittings, we get power outlets, then we want we'll call it circuit cabling, the underground ducts, that'll be a length, kind of, yes, and the roof duct. That's pretty much all the key quantities that we want to go through the drawings and we want to calculate. So to begin with, we'll go back to that electrical layout and let's just make sure we've got all these. Shall put down metering point, 30 points. Let's just double check that you've got everything and cabling, sorry. But that can start and we'll record quantity number. So there's one distribution board. Next we want to get all the different types of light fittings, but remember they've given us all this information ready to take from here, so we don't actually have to go calculate it individually. So we'll just set it light fittings. We'll break those down into two types. What's the terminology? We call it a ceiling light and a wall light. Yeah, if they didn't give you this information in the table, it'd be easy just to go through the drawings and count them up. Since we've already got it in the table, we'll just take it from here. So there's 5 of the ceiling lights, 2 of the wall lights. Then for the power outlets, they're just wall double sockets. Rename that for double sockets. The wall double sockets, there's... Sorry, we should get switches as well. I missed that. So 5 switches, which would come under lighting. And then for the wall double sockets, there's 5s. I already had cabling there. So let's just call this cabling. And what are the different types of cabling? AWG 14, AWG 12, and then we'll call it the mains cabling. Now this drawing has, again, I don't think it's got a scale on it, but we know the length of building. So I'll just quickly calibrate. So how long is the building? Building is 11059 plus 3.88. Yeah. 14.147. So we know this length. Tools, set scale, custom. How long is it?
14.1%.
So that's the internal lengths. Then we have to get the external lengths as well. So we can get those from another drawing. We know the mains cabling is going to run from that corner to that corner. So you can just simply go to this drawing. With the same if we know.
Let's have it set it up. I can cut this off.
It's 36.9 meters. And when we're doing cabling, we want to allow generally we will allow 2 meters at either end for terminations. So we go equals 2 meters either end for terminations. So we go equals and 5% for wastage. Plus 2 by 2 times 1.05. So it would be 43.05 meters. The mains cabling. What other external cabling is there? Then we'll just do this one circuit by circuit. So C1, C2, same.
Attend to the bleeding. Front.
So R and C7. C7 is going to be 36 meters.
The ball. Right.
So let's work out. So C, I'll just put the actual lengths here and we can apply termination lengths to it after. So it'll be equals this plus 4, because you've got terminations at both lengths, times 1.05. So that 5% wastage. And then we'll get the actual length. So C1, that right to that, so 13 meters plus to that switch, so for C1 that gives us a total length of 13 plus 7.5 plus 5.5. 17 plus 7.5 plus 5.5. C2. The C2. C2 goes, look, okay. Goes from here,
Yeah.
That's 11 meters. C3 is going to be here. The tanks. 16 meters. C4. Next for C4, which is try and C4.
Oh.
C4 is the garage door engine. So it's that one. Which they've labelled it C5s. I think it's wrong. 7.9.
So go at
8 meters. And then C5 is... his labels aren't correct, which is a little bit confusing, but at the end of the day, it doesn't matter as long as the quantities are correct. In 2 meters for that. 2 meters, and we'll just apply the same formula. Sorry, that's the C6, and C6 is the power to
solve.
C6 was C7, same thing. A little bit confusing because these labels are wrong. But
Just call out 3
meters. Delete those, and then we've got our lengths of the different cablings. Now, could go and do all these duct lengths in detail, but I'll skip that because the principle is the exact same. We're just measuring lengths. So I'll just also fill out that we've got 1 metering point and 2 earthing points. And that's our electrical quantities. Then for our hydraulics quantities, the principles are actually exactly the same. We've just got to go through the drawings, count up the number of different floor drains, fixtures, bends, lengths, and add them into a bill of materials. So the takeoff principle is exactly the same. It's going to involve measuring all these lengths, counting the number of valves, counting the number of fixtures, and adding them to a table. So I won't go through and do that for the hydraulics. That's something I'll leave for you to do. And yeah, the principles are all exactly the same. It's just measuring lengths, calculating quantities. So we've covered the key items. We've covered earthworks, concrete structures, services, and architectural works. But we also need to give consideration to some other key items that when you're completing quantity takeoff, you need to consider. So we'll finish off section 3 by talking about some of these other items that don't fall into one of these main categories. In this section, we're going to talk about temporary works, site facilities, and safety and environmental considerations. And because these items vary so much from project to project, we're not really going to do a detailed example, but we're just going to talk broadly about what you would consider when documenting and calculating these key quantities. Temporary works are any non-permanent construction works that are needed to facilitate the permanent construction works. So for example, say we're pouring a 5 meter high concrete wall. We'll need to get scaffold to access up to this height, and we'll need to get propping to ensure the formwork's properly supported. These materials can come at a significant cost, so need to be considered in our estimates, and therefore we need a way of quantifying the amount of work there has to be done. To accurately calculate temporary works quantities, we need to understand the construction methodology in detail, so we need to actually understand how something's going to be built. We need to refer to a temporary works design. So this is a set of engineering plans that refer specifically to how the temporary works are going to be built. So for example, if we're talking about a 5-meter high concrete wall that we need to erect scaffolding up to, we'll need to refer to the temporary engineering works drawings to quantify the amount of scaffold. So if we're looking at scaffold as an example, we'd calculate the area of scaffold in meters squared, and then get the volume based on dimensions of the scaffold, and then potentially have several access towers to reach the highest points of the scaffold. So there's lots of different types of temporary works that we have to consider. So scaffold's just one example, but the general process for estimating or quantifying temporary works is we need to understand the construction methodology and then refer to the temporary works design to calculate the key quantity we need. The next item we need to consider are any non-permanent site facilities. So these are things like crib rooms, offices, or toilets that we need to set up to facilitate the construction works. Again, like temporary works, these can come at a significant cost to the project, so we need some way of accurately quantifying them. So in the same way that when we were talking about temporary works, when we're talking about site facilities, we need to understand the logistics and running of the construction site. We need to understand things like the peak number of workers on site to accurately size the lunchrooms, and then we overall need a logistics and site running plan. We'll then be able to refer to this plan to calculate exactly what site facilities we need. So for example, if our site is 50 meters by 50 meters, we might have to allow to erect temporary fencing around the site to keep it secure at night. For that example, we'd just simply do a linear measurement calculation. The other important thing to understand when we're talking about site facilities is we need, as they're non-permanent, is we'll also need to understand hire durations, which we'd be able to find in the project schedule. And the final other item we need to consider when running our construction project are environmental and safety considerations. So in the same way that we need temporary works and we need site facilities, our construction project will almost certainly require safety and environmental equipment. So for example, we might need signage at the front of our construction site to show who the key site contacts are and what the working hours are. We might need safety barriers. We might need to put fire extinguishers around the site. And these we'll have to get from our safety management plans and safety site setups to accurately calculate the quantity of all the items that we're going to need for our project.